Hello there and welcome to Life Beyond Seen, where curiosity slows down and the world settles into a softer focus for a little while. Tonight we're taking a quiet step towards something that hides in the calmest corners of the sea, places so peaceful on the surface that you'd never suspect what waits below. They look like nothing more than circles of darker water, patches of deep blue surrounded by the lighter shades of the shallows, almost like the ocean simply forgot to match its colours. But beneath those unassuming openings lies something far stranger. They drop straight down through limestone and ancient seabed like natural shafts carved into the past, places divers describe with a mixture of fascination and a hint of the same worry you feel when the floor creaks in an empty house. These are blue holes, and tonight we're drifting slowly toward their edges to see what thrives inside them. What kind of life manages to survive in conditions that should by all rights send everything running the other way? Before we sink beneath the surface, I'd love to know where you're listening from right now. Is it evening for you? Early morning? Maybe you're somewhere in the middle of the day and just decided you needed a moment of quiet. Wherever you are, thank you for sharing this moment. And if you find this kind of gentle exploration soothing or interesting or simply a nice way to relax after a long stretch of whatever today asked of you, I'd be grateful if you liked the video or subscribed. It helps this little corner of calm reach someone else who might need a soft voice helping them drift away from the noise for a bit. We're not rushing. There's no reason to. Blue holes have been waiting for thousands of years, hidden beneath tides and storms, and they haven't grown impatient yet. They sit quietly in places like the Bahamas, Belize, the Red Sea, and the coastlines of Australia, shaped long before humans laid eyes on them. Many began forming during ice ages when sea levels dropped and exposed limestone caves to the air. Rainwater, slightly acidic from dissolved carbon dioxide, seeped through the rock and carved out deep vertical shafts. When the ice sheets melted and the oceans rose again, those caves flooded, trapping their strange architecture beneath the waves. What we see now from above is only the doorway to something that was once carved in dry darkness, a place that used to echo with the drip of water rather than the soundless weight of the sea. If you're standing on the deck of a small boat in a place like the Bahamas, you'd barely notice anything unusual. The water shifts gently, sunlight flickers across the ripples, everything looks as calm as a postcard. But then the boat drifts over one of these openings, and suddenly the colour changes. It's a sharper blue, almost a sudden plunge in colour rather than depth, like someone cut out a perfect circle and swapped the water underneath for a different ocean entirely. People who see it for the first time often describe the same quiet pause. There's nothing dramatic happening, just a simple shift in colour, but it taps something instinctive. A darker hole in the ground usually means don't go in there. A darker hole in the ocean feels even more unsettling because you can't see where it ends. But we're not hurried. We're just letting the colour deepen beneath us. The water warms your skin on the surface, but with every imagined metre of descent the world cools. The shape of the daylight above grows softer. The bright blues of the shallow reefs fade into a muted wash. This first stretch beneath the surface still looks like something familiar. Fish dart by in small groups, bright enough to seem like bits of sunlight that got lost on their way back up. The walls are rough pale limestone, the same colour you'd expect if you walked through a dried cavern, except now everything is softened by water. The quiet begins almost immediately. Even if fish swim past you in nervous clusters, the sound never carries the way you expect it to. There's no echo, no sense of space responding to movement. Blue holes have a way of swallowing sound without effort. Divers often comment that it feels as if the water itself is listening but not answering. Not eerie exactly, just deeply, strangely private. If you keep descending in your mind's eye, you pass layers of water that don't want to mix with each other. It's something that surprises most people the first time they hear it. Water is water after all. Why wouldn't it blend together? But in blue holes, the boundaries between layers are sharp. Warm, oxygen-rich water sits near the top. Then somewhere below it, the composition changes. The salinity increases. The temperature shifts. The oxygen thins out until eventually it disappears entirely. Below that boundary lies an anoxic zone, a stretch of water that should be completely hostile to anything living, and yet life persists there, just not in the form people expect. But I'm getting ahead of myself. We're not going into the deeper zones yet. Right now we're still drifting downward through the area where most divers stay. The region where fish that normally roam the surrounding reefs venture just inside the opening to forage. Sometimes groupers hover motionless in the dim. Sometimes schools of silversides swirl in looping formations that catch the faint light in synchronized pulses. The motion is steady and unhurried, almost as if everything here is conserving energy. The deeper you go, the more the fish seem to understand that this is not a place where wasted effort ends well. Some blue holes connect horizontally to larger cave systems, others descend vertically without branching. A few have debris cones at the bottom from centuries of storms sweeping material into the opening. But no matter the shape, the feeling is similar. The walls rise above you like a cylinder of stone. The entrance to the world above becomes a shrinking circle, and slowly, almost without noticing, you begin to feel the weight of a place that doesn't behave like the surrounding ocean. If you were actually diving here, you'd notice the light thinning. Your vision becomes more focused, not because the world narrows, but because your mind does. When the environment removes distractions, your thoughts slow. It becomes easier to pay attention to details you might normally overlook. The texture of the limestone, the faint vibration of something far away, the way a single fish investigates a crack in the wall with a confidence it probably shouldn't have in a place where predators hide much deeper down. Blue holes aren't just deep, they're chemically unusual. Many develop layers with wildly different compositions stacked right on top of each other. These layers rarely mix because the openings are too narrow for strong currents to sweep through them. Each layer becomes its own miniature world. Near the top, the water is similar to the surrounding sea. Farther down, it becomes richer in hydrogen sulfide, a gas toxic to most marine life. Then below that, the water might turn completely anoxic with no oxygen at all. It sounds like a recipe for emptiness. But instead, it's one of the strangest examples of life adapting to conditions that seem almost deliberately inconvenient. Before we reach those depths, though, it helps to understand why these places are so isolated. The entrances to many blue holes are narrow, sometimes only a few meters across. Storms can push water across the surface, but powerful currents rarely reach inside. Without mixing, the deeper water becomes cut off from the normal rhythms of the ocean. No tides to sweep nutrients in, no waves to churn oxygen downward, no sunlight once you're deep enough. It's the sort of environment where evolution either gives up entirely or goes in a direction no one expects. Even now, as we drift deeper in this slow, imaginary descent, we haven't yet reached the point where the world changes completely. But the shift is coming. You can almost sense it in the way the water temperature drops slightly, or how the light becomes less interested in reaching you. Up above, the opening looks distant, but not alarmingly so. Down below, the darkness thickens with the steady confidence of a place that's been practicing darkness for thousands of years. Blue holes have fascinated scientists for decades because they preserve conditions long erased from the rest of the ocean. In some layers, the chemistry resembles ancient seas from hundreds of millions of years ago. Life thrived in those conditions long before oxygen became abundant in the atmosphere. So when researchers lower instruments into these deep pits, they're not just sampling water, they're sampling time. They're finding microbial communities that mirror early Earth, creatures that have abandoned the luxury of oxygen and turned instead to forms of metabolism most animals could never tolerate. But for now, we're still hovering above that transition point. A few more meters down, and the typical marine creatures you'd expect to see begin to thin out. Reef fish slip away first, preferring the sunlight and the predictable structure of the upper shallows. Larger animals pass by from time to time, but they rarely stay. The environment grows too stable in one sense and too unpredictable in another. Some predators learn to use the edges of blue holes as hunting grounds. because prey becomes disoriented when the terrain changes so suddenly. But the deeper regions aren't their territory. Even sharks, which sometimes glide across the openings, avoid dropping too far below the point where visibility disappears. And this quiet, steady descent gives us a chance to understand why these places captivate people. They're dangerous, yes, but not in a dramatic way. The danger is subtle. There's no monster waiting in the dark. No sudden drop-off you didn't expect. The risk comes from the way the environment shifts. The air you carry with you behaves differently under pressure. Your body responds differently. Your mind might misjudge distances or directions. It's a place that rewards attention. And attention, ironically, is something these deep, still spaces encourage naturally. There's also a strange sense of being somewhere untouched. Many parts of the ocean feel alive with movement, sound, and activity. But blue holes feel like sealed vaults. They preserve things. They hold on to secrets. Fossils, sediments, ancient water chemistry, even the remains of species that no longer swim through today's oceans. Some blue holes on land have preserved the bones of early humans, extinct animals, and even plants that once lined the coasts before the sea rose and claimed those caves. Underwater blue holes do something similar with microbial life, but instead of bones, they store chemical histories. And slowly, as we keep our steady downward drift, the world begins to change shape in the way it feels rather than looks. The water clouds slightly. A thin haze forms around you. It's not dangerous on its own, just a sign we're nearing a boundary. If you stayed here long enough and watched closely, you'd see small particles drifting upward or downward depending on which layer they belong to. You'd see the faint outline of a thermocline where temperature shifts over a surprisingly short distance. And if you reached out with a hand, you might feel the difference. Not harsh, just present. This is where the light above still reaches you, but the deeper world below becomes harder to ignore. We're almost at the point where the normal rules of the ocean start giving way to something else, something that doesn't rely on sunlight, oxygen, or the usual rhythms of day and night. The creatures living farther down follow strategies shaped by chemistry rather than light. They feed in ways that would make little sense anywhere else. They're adapted to stillness, to an absence of mixing, to a kind of quiet that the open ocean rarely offers. We're not going any deeper yet. We're just settling here for a moment, letting the details of this threshold settle in. The surface is still visible. The darkness below is still patient. And in this space between them, the story begins to shift toward the lives that manage not only to survive in these pits, but to thrive in ways that make you question what life actually needs to function. From the surface, blue holes almost seem determined to keep their secrets quiet. If you were drifting across one in a small boat, or even standing on a beach nearby, nothing would alert you to the idea that the seafloor beneath you suddenly drops away like an elevator shaft carved into stone. The water above them looks calm, as if someone placed a single patch of stillness in the middle of an otherwise restless sea. Even when the waves are rolling and shifting in every direction, the water that hovers above these openings often behaves differently, shaped not by surface winds but by the unusual geometry below. Divers talk about the moment they glide over the boundary, that slight hesitation in the water's movement where currents soften and the feeling of drift becomes heavier, as though the ocean itself takes a slower breath here. If you happen to be snorkeling above one of the openings, the first sign that something is different would be the change in colour. The shallows around a blue hole glow with bright turquoise, the kind of colour associated with travel magazines and postcards, made even more vivid by white sand scattering sunlight back upward. But then the brightness cuts off in a near-perfect line. The water beneath you deepens into a darker shade that looks almost painted, like the sea is showing you a doorway without explaining what lies behind it. The contrast is so stark that even people who know nothing about blue holes instinctively pause, wondering why the water suddenly seems unwilling to let light pass. Some visitors describe a kind of instinctive response, not fear exactly, but an awareness that they're above something more significant than it appears. Humans tend to read landscapes and waterscapes for hints of safety or danger, and a sudden change in colour, especially one that drops into near blackness, triggers the same kind of attention spike you'd feel when walking from a well-lit hallway into a dark room. Even if nothing is physically threatening you, your senses shift gears. This shift is subtle, but noticeable enough that many researchers studying these places mention it in their field notes. You know something is beneath you, you just can't see it. Strangely, the calmness above these openings makes the contrast even sharper. The ocean gives plenty of warnings in most situations. Riptides churn the surface, reefs create splashes where waves break, shallow sandbars ripple with telltale patterns, but blue holes don't provide such noisy clues. You could circle one for an hour and never guess at the complexity hidden below. Fishermen in certain regions used to avoid dropping nets or anchors across them, not because they understood the science of the structures, but because they knew from observation that the water changed abruptly in those spots. The loss of equipment wasn't worth the risk, and the unusual stillness above them made the spaces feel unpredictable even during calm tides. Scientists who study these places often begin their descriptions the same way. They note the visible surface, the ring of pale sand around the perimeter, the deeper blue in the centre, and the overall impression that the ocean is holding its breath. That stillness is the first clue that something unusual is happening beneath the top few meters. Currents lose their strength, waves lose their grip, movement loses its enthusiasm. The sea above a blue hole behaves as if it is sliding across a glass table rather than a textured landscape. The physics behind this are simple but profound. Because the seafloor drops away so sharply, the shallow bottom that normally interacts with waves and breaks them apart is suddenly absent. There's nothing to stir the water or pull energy downward. The surface floats above a void, and the result is a patch of calm in a place where calmness shouldn't logically exist. If you were to watch from above long enough, you might notice that fish behave differently here too. Some species avoid the edges, others treat the perimeter like a natural boundary line, circling but rarely crossing into the darker water unless they have a reason. It's not fear that keeps them back. Fish respond to temperature, light, and pressure differences far more than to shapes or shadows. And these openings represent a change in nearly all of those conditions. Light falls away faster, the temperature may shift slightly, the pressure gradient increases more steeply. For many species, dipping into that darker region doesn't align with their instincts for feeding or shelter, so they skirt the threshold and return to familiar territory. People have fallen into the habit of describing blue holes as hidden or secretive, but that wording isn't entirely accurate. They aren't hiding. They simply don't draw attention to themselves. They don't roar, churn, or glow. They don't leak bubbles or produce strange sounds. They just sit quietly under the surface, waiting for the right pair of eyes to notice the difference. The stillness is almost the point, a reminder that the ocean doesn't always announce its depth or complexity. Sometimes it prefers understatement. If you imagine standing on a paddleboard above one, the sensation is even clearer. Your shadow might appear crisp along the pale bottom if you're near the perimeter, then suddenly elongate into a blur as soon as you drift over the opening. The visual reference points vanish. You no longer see sand or coral beneath you. Instead, you see a gradient of blue that deepens so quickly it feels more like a sky than a seafloor. Many people describe the sensation as floating above a drop-off, even though they are still on the surface. It's a disorienting experience, mild but noticeable enough to make even confident swimmers pause and take a breath before continuing. The stillness isn't limited to the surface. The first few meters below are the transition from the familiar shallows to the environment that defines the blue hole. If you were to hover just beneath the surface, the world would sound muted. In normal, shallow reefs, sound travels briskly. You'd hear crackling from snapping shrimp, the occasional clatter of parrotfish grinding coral, and the shifting movement of sand stirred by fish. But above a blue hole, many of those noises fade. The open shaft below doesn't resonate sound the same way a flat seafloor does. It absorbs vibration rather than reflecting it, letting noise fall downward through the shaft rather than passing it back to your ears. This absence of sound is striking enough that divers often comment on it in journals. It creates an unusual sense of privacy. Even if you're diving with a group, the water around you feels thick with quiet. Movement seems smaller. Breathing becomes the loudest thing in your world. Instead of the bustling noise common in coral environments, you get a still, steady silence broken only by bubbles drifting upward. That quiet sets the stage for everything that follows in deeper regions. But even here near the surface, the atmosphere shifts. It's tempting to imagine that anything unusual must look unusual, but blue holes push against that assumption. If anything, their stillness gives off a deceptive normalcy, the sort of everyday calm that encourages you to think nothing urgent is happening. Only once you pay attention do you see how the water behaves differently than the surrounding sea. Boats don't bob as much. Fish don't dart as quickly. The faintest breeze loses some of its effect on the surface. Even birds passing overhead seem quieter, though that's likely coincidence more than science. Still, everything around the opening appears more composed. Researchers in certain regions have measured minor differences in temperature, salinity, and current velocity even in the uppermost layers, but these differences are subtle. Nothing extreme enough to cause dramatic surface anomalies. Instead, they create a kind of gentle barrier, a zone where the normal flow of the ocean slows just enough to create an impression of stillness. It's the same effect you'd notice at the edge of a sinkhole or a deep well on land. The structure is so sudden, so vertical, that the movements around it change without outward force. Some of the calmness actually comes from the shape of the opening itself. Many blue holes in the ocean begin with a circular entrance surrounded by shallow shelves. These shelves act like natural bowls. Waves break farther out, but their energy disperses as they move inward, leaving the central area undisturbed. The shelf acts as a physical buffer, a kind of gentle perimeter that prevents heavy motion from entering the pit. The result is a visible ring of slightly choppier water, fading into a centre where ripples flatten out again. For people who have spent time on the water, these clues become intuitive. The sea communicates through movement. When it stops moving in the way you expect, it's telling you something has changed below. Not loudly, just matter-of-factly. All you need to do is watch. The stillness also contributes to the illusion of safety. You see a calm surface and assume the water beneath is equally manageable. Many divers underestimate the depth at a glance, because the opening hides it so effectively. Blue holes drop straight down, sometimes hundreds of feet, sometimes more. The visual calmness on the surface doesn't correlate with the physical reality below. It's one of the few places in the ocean where quietness signals not simplicity but complexity. Local communities in regions like the Bahamas and Belize have long incorporated blue holes into their stories and traditions. Some viewed them as gateways to the spirits of ancestors. Others considered them homes for sea creatures rarely seen in open water. These stories weren't born from dramatic surface features. They came from the knowledge, passed down generations, that the calm surface concealed something deeper, stranger, and potentially hazardous. When you don't see waves breaking, you assume depth. But when even the wind seems to lose confidence over the opening, it becomes something else entirely, an invitation to wonder, with a hint of caution. In the scientific community, blue holes are often described as natural laboratories. Their still upper layers protect delicate chemical gradients, preserve microbial communities, and maintain water trapped there for long periods. The lack of mixing means the water below might represent conditions from a different era. If the ocean around them is constantly stirred by tides and storms, these openings are like still rooms in a moving house. They hold on to the past in a way that the rest of the ocean doesn't. But none of that complexity is visible from the surface. You only get the stillness, the quiet, and the sense that the ocean becomes more reticent here. If you were to swim slowly across the edge, the feeling would shift gradually but unmistakably. The bright sand and coral beneath you would slip out of view. Light would scatter differently. Your depth gauge might show only a few meters at first, then suddenly drop faster than expected as the limestone shelf ends. In many places, the walls of the opening are undercut, meaning the hole is broader beneath the surface than it appears from above. The surface gives the impression of a neat circular opening, but the structure widens like an inverted funnel. What you see from above is only the smallest portion of the full cavity. This widening structure contributes to the quietness. Sound that enters the opening diffuses rather than bouncing back. It's not an echo chamber, it's the opposite, an absorber. Even your heartbeat feels louder because nothing below returns the sound. Divers sometimes report that their sense of depth becomes skewed in these early meters because sound cues disappear. The human brain unconsciously uses acoustic reflection to judge space, and without those cues, the world feels muffled and undefined. The surface stillness also shapes temperature patterns near the entrance. The lack of strong mixing means warm water lingers in the upper layer longer than it would elsewhere. Beneath that, the temperature can shift quickly, creating a layering effect that resembles the experience of stepping from one room into another. It's not dramatic enough to shock the system, but noticeable enough that divers mention the change even without instruments. This layering becomes more extreme farther down, but even at the top the structure begins announcing its complexity quietly. The stillness above blue holes is like the introduction to a long story. It doesn't reveal the plot. It simply sets the tone. It prepares you for a world that shifts gradually from ordinary to unusual. Nothing happens abruptly. There's no sudden change in noise or motion. Instead, the water slopes into quiet the way twilight slopes into night. By the time you realize how different the environment is, you're already past the point where the surface feels familiar. You've crossed above the boundary without noticing the threshold. And even though the calm surface looks peaceful, it's only the beginning. Beneath it, the water begins layers of increasing strangeness, conditions that challenge typical definitions of what underwater life needs. But before moving downward, it's worth lingering on the idea that something so dramatic can hide beneath something so ordinary. Blue holes don't advertise themselves. They rely on simplicity to disguise depth. And in the ocean, few things draw more attention than a place that seems to avoid drawing attention at all. The first hint that the descent is truly beginning comes when the last traces of the ocean floor stop appearing through the dimming blue above the opening. In the shallow perimeter, everything looked familiar enough, even if the water's behaviour felt subtly different. But once you ease past the rim and commit to moving downward, the environment starts changing in ways that don't announce themselves with any kind of drama. It happens quietly, almost politely, the way a room seems to darken not because someone flipped a switch, but because the sun shifted behind a cloud and you only noticed after the fact. You find yourself surrounded by open water that thickens with depth, not like a fog, but like a weight that presses gently against the edges of your awareness. The walls of the blue hole appear at first as pale outlines, visible only when your light or the faint ambient glow of the surface catches them. They drop straight down with a precision that feels unnatural for something carved by ancient rainfall. Limestone doesn't usually behave so neatly, yet here the edges form a clean circle descending into the deeper void. If you reach out and run a glove across the rock, you'll feel the texture of a cave that once held air instead of water, formed long before the sea reclaimed it. That shift from air-filled space to submerged darkness sets the stage for everything to come. You're not entering a trench carved by underwater currents. You're entering a fossil of the Earth's past. As you drift downward, your field of vision narrows, not because you're losing sight dramatically, but because the colour spectrum begins to thin out. Red disappears first, though you don't notice unless you brought something bright to test it with. Then orange fades, then yellow, until the world settles into gradients of green and blue that slowly collapse into darker shades. Even sunlight, which seems so dependable up at the surface, reveals how little enthusiasm it has for deep descent. It follows you part of the way, then gives up as though deciding that whatever waits below is not its concern. Divers often talk about the point where the surface stops feeling like a reachable place. It's not a matter of depth alone. It's the moment you turn upward and notice that the bright circle above has shrunk. The edges of the opening blur slightly as the refracted light dances around them, and for the first time, the space feels less like a swimming pool and more like the entrance to an entirely different environment. There's no fear in that moment unless you brought it with you. Instead, there's a steady sense of leaving one world and entering another, guided by nothing more than slow movement, changing light, and a silence that becomes thicker the farther down you go. The upper water still holds oxygen, but even here you can sense that the supply is thinning. Life begins adjusting. Fish that darted easily near the entrance become less common. You might see a solitary snapper or a passing jack, but they rarely stay long. Creatures adapted to bright reefs or shallow seagrass beds don't linger in places where the rules change so abruptly. Their instincts push them back toward the safety of sunlight and familiar terrain. They graze in the transition zone and then retreat before the chemistry shifts too sharply. If you stop moving and allow yourself to hover, the water feels unusually still. Even in the open ocean, water moves constantly, nudging you, carrying faint pulses from unseen sources, pushing tiny particles in steady lines. Inside the blue hole, these cues diminish. The water doesn't swirl, it doesn't tug, it simply surrounds you, patient and neutral. You're drifting in a column where movement is controlled almost entirely by your own choices. The ocean outside is dynamic. This place is static. That difference becomes easier to feel as the depth increases. One of the most surprising changes during descent is how sound behaves. At the rim, you could still hear faint crackles from outside reefs, or the shifting motion of schools of fish. Down here, each meter strips those sounds away. The limestone walls absorb vibration, and the geometry of the shaft pulls noise downward rather than across. Your breathing becomes the loudest thing you hear, rhythmic and steady, echoing inside your mask and equipment rather than through the environment. Without outside sound cues, your brain focuses on small things you wouldn't normally notice. Your heartbeat, the bubbles rising past your ears, the distant creak of gear adjusting to pressure. This sensory shift creates a kind of internal quietness that mirrors the external silence. As you continue downward, the world darkens not just in colour but in density. The water takes on a slightly hazy appearance, like a faint mist suspended in liquid. This isn't actual sediment but the beginning of a boundary zone students of blue holes know well. The water layers here are still oxygenated but begin interacting with deeper chemistry. Tiny particles drift upward and downward depending on the gradients forming below. If you wave a hand, they scatter, then settle again in slow measured movements, as if reluctant to respond. Some divers describe this zone as the moment when the throat of the blue hole begins to tighten, not physically, but perceptually. The circular walls narrow slightly as your light reveals how the undercut structure widens beneath the surface. What looked like a perfect circle from above now reveals its hidden geometry. The further you descend, the more you realise the hole is larger beneath the surface than it appeared. It extends outward in subtle slopes and ledges carved long ago by dripping water and collapsing limestone. You're no longer inside a narrow tube. You're in a massive vertical chamber that simply hides its size well. This sense of enclosure, even in a widening space, is partly psychological. Humans are not built for vertical voids. We rely heavily on visual reference points to understand scale, orientation, and distance. When those references fade, the brain starts improvising. That improvisation often results in mild disorientation if you're not paying attention. You might feel as though the walls are moving closer when they're not, or that the descent is slowing when it's actually steady. The throat of the ocean does not behave like open sea. It behaves like a location with its own rules of depth, perception, sound, and motion. Temperature begins to shift as well. The warmth of the surface recedes, replaced by a gradual drop that doesn't shock the system but becomes noticeable after a few minutes. This cooling signals the transition from surface-fed water to a more isolated region. Since blue holes don't mix like the surrounding ocean, these layers build distinct thermal profiles. The deeper you go, the more sharply the temperature transitions occur. But right now, the change is only the beginning, a hint of the more dramatic shifts waiting farther down. If you shine a light ahead, the beam cuts through the darkness but doesn't travel far. The water absorbs it quickly. Your world narrows to whatever the beam touches. The rest becomes an undefined space that neither invites nor repels. You drift downward, knowing the light you carry is no match for the depth, but also knowing it doesn't need to be. You're not trying to illuminate the whole place. You're trying to understand how it changes. Eventually you reach a depth where the last reef-associated fish fade completely. The community here has adapted to reduced visibility and fewer resources. You might see small crustaceans or sluggish, mid-water organisms drifting in slow patterns, conserving energy in a place where oxygen demands high efficiency. Their movements are sparse and oddly dignified, shaped by constraints that don't apply in the open ocean. The limestone walls reveal grooves and irregularities that tell their own story. Some are the remnants of dripstone formations that once hung in air-filled darkness, long before rising oceans drowned them. Others are marks from collapses that shifted the architecture of the whole, creating shelves, slopes, or pockets where organic material gathers. These pockets often become feeding grounds for small organisms drawn to the nutrients trapped there. Even in a place defined by stillness and isolation, life finds corners to occupy. As you descend farther, the darkness matures. It's no longer the dimness of late afternoon underwater. It's the kind of darkness that forms when sunlight loses interest entirely. This isn't hostile, it's simply indifferent. Humans often think of darkness as a threat because it hides information, but in blue holes, darkness is more like a neutral presence. It doesn't rush to meet you, it just exists, waiting for whatever descends through it. One of the remarkable things about this phase of the journey is how seamlessly it shifts from familiar to unfamiliar. There's no clear boundary, no signpost saying you've crossed into the deeper domain. Instead, each meter brings a slight adjustment. Each adjustment accumulates, and by the time you pause to look around, you realize you're in a place where the normal expectations of the ocean no longer apply. The throat of the blue hole has accepted you quietly, not as a guest or an intruder, but as another presence passing through. The deeper regions begin to hint at the darker chemistry below. If instruments were lowered alongside you, they would begin detecting slight changes in dissolved gases, particularly the first traces of hydrogen sulfide beginning to seep upward. These concentrations are still low enough to be harmless to a diver, but signal that the boundary between oxygenated and anoxic water is approaching. The throat of the ocean is not uniform. It's layered with invisible transitions that only become apparent when measured or experienced physically. Movement becomes more deliberate here, not because of difficulty, but because the environment invites slow observation. Rapid motion feels out of place. The descent encourages calm awareness, not haste. Every few meters brings slight shifts in lighting, temperature, microbial presence, and suspended particles. Taking time to absorb these changes makes the descent feel more like a gradual introduction, rather than a plunge into the unknown. There's a moment when you look down and see nothing but darkness, even in the path of your light. This isn't because the water is opaque, it's because depth has outpaced illumination. What lies below is still open water, but the light can't reveal it yet. Your eyes adjust, your breathing remains steady, and you continue down, trusting that the throat of the blue hole is shaping your experience one sensory adjustment at a time. The boundaries between layers are still ahead. The microbial mats, the hydrogen sulfide clouds, the zones where oxygen disappears completely, all of that awaits deeper down. But right now, you're in the long descent through the quiet center of the structure, where the surface is far above, and the deeper world is coming gradually into reach. Nothing down here rushes. Nothing demands urgency. The water simply thickens with meaning, and you keep drifting toward the next layer waiting in the dim. There comes a moment during the descent when something changes in a way you can't quite see, yet you feel it. The water has darkened, the temperature has cooled, and the faint noise from the upper ocean has dissolved completely. But now the shift is more than sensory. The boundaries between the living conditions you're familiar with and the ones you're about to enter begin to sharpen. The world above relied on oxygen. Every fish that passed by you in the earlier layers, every coral fragment that clung to the rim, every drifting organism that depended on the water column for movement, all of them existed within a range where oxygen was plentiful enough to sustain their metabolism. Down here, though, that rule begins to lose its authority. If you were able to glance at a meter tracking dissolved oxygen levels, you'd see the numbers sliding downward inch by inch. At first, the drop looks slow and unremarkable. Then the curve steepens. Oxygen becomes scarce, not just reduced, but nearly absent. By the time you reach the transitional layer, the zone below you might contain almost none at all. It isn't merely low, it's missing. This is where a normal marine ecosystem would collapse. Fish would suffocate, most crustaceans would fail, plankton would struggle. And yet this is where life begins shaping itself in ways that seem specifically engineered for an environment that rejects the usual blueprint. As you sink deeper, the first sign of the coming transition appears as a faint cloudiness. At a glance, it resembles silt or sand disturbed from below, but this haze is organic. It's microbial. Suspended microorganisms form a thin, uneven veil that stretches across the blue hole like an uninterrupted blanket. The layer isn't perfectly defined, and it doesn't respond much when your movement disrupts it. Instead of dispersing dramatically, it shifts slightly, then drifts back into formation with a kind of calm persistence. You're encountering a living boundary line, made up of cells that have adapted to survive where oxygen has no influence. The organisms that dominate this environment aren't the kind of life forms most people imagine when they think of the ocean. There are no bright colours, no quick motions, no familiar shapes. Instead, the life here is microscopic, ancient, and relentless. These microorganisms thrive on chemical processes that existed long before Earth's atmosphere held much oxygen at all. They don't rely on the gas we breathe, they rely on chemical gradients, differences in dissolved compounds that allow them to transfer energy through pathways most animals would find toxic. Some rely on sulfur, others rely on methane, nitrogen, or iron compounds. The specific mixture depends on the individual blue hole, because each one develops its own chemistry over thousands of years. What they all share is the ability to exist in places where the water above cannot safely mix with the water below. They occupy a metabolic niche that feels more like something from the deep past than the modern ocean. If you reach out toward the haze, your light will reveal the density of the microorganisms suspended in the water. They gather around the invisible border where the last traces of oxygen collide with rising hydrogen sulfide from below. This boundary is the perfect environment for bacteria that survive by oxidizing sulfur compounds. To most marine life, hydrogen sulfide is a threat, a toxin that interferes with cellular respiration and quickly becomes lethal. But down here, it's a resource. The organisms treat it the way surface ecosystems treat oxygen. It's not a poison for them, it's fuel. Passing through this microbial layer is like moving from one world into another. The water takes on a milky quality for a moment, then clears again as you enter the zone where oxygen is effectively gone. This depth varies between blue holes. In some, the shift begins tens of meters below the surface. In others, it might occur far deeper. But once you cross that threshold, you're no longer in water that supports typical marine life. Everything tied to oxygen, metabolism would fail here. And yet, life endures. Microbial mats form along the limestone walls, clinging to surfaces in irregular patterns. These mats spread in patches, their presence shaped by whatever chemical gradient or nutrient source happens to drift past that spot. If you move your light slowly across the stone, you'll see layers of texture where colonies have built themselves into thick, cohesive communities. Some appear pale white, others take on muted shades of yellow or brown depending on their metabolic pathways. These colonies aren't decorative. They're hard-working engines of chemical transformation, converting unusable or toxic compounds into energy through biochemical routes inherited from some of Earth's earliest ancestors. The deeper you go, the more pronounced these communities become. In some places, they form long filamentous structures that wave gently in the stillness, despite the lack of noticeable current. These threads are microbial structures, not plants or organic debris. They form from bacterial species that build mats with physical extensions, allowing them to interact with specific pockets of dissolved compounds more efficiently. The motion is subtle, almost imperceptible without focused attention, but it's enough to remind you that even in silence and near total darkness, things here remain active. Below the microbial boundary, the water has changed in composition more than in appearance. There is no oxygen. Hydrogen sulfide levels increase dramatically. The smell would be overwhelming if the water were exposed to air, but here the concentration remains dissolved. Sulfide-rich water feels slightly different to the skin, though that difference lies more in psychological response than physical sensation. You know you've entered a zone incompatible with your own biology, and that awareness shapes your perception of every movement. The water seems thicker even though it isn't. The organisms thriving here have no need for oxygen. Instead, they rely on anaerobic respiration, a form of metabolism that uses alternative electron acceptors. Some use sulfate, some use nitrate, some use carbon dioxide. This metabolic flexibility allows them to operate under conditions that would stop oxygen-breathing organisms immediately. What looks like an empty void is, at the microbial scale, extremely active. It's not just single-celled life that appears in these conditions. Certain simple multicellular organisms have been discovered surprisingly deep within blue holes, residing in environments previously assumed to be completely inhospitable to anything but bacteria. These creatures are tiny, often transparent or colourless, and move with slow, unhurried motions. They aren't fast because speed offers no advantage here. The water doesn't churn. There are no predators chasing them with speed. Their existence is shaped by patience and chemical opportunity, not agility. Some species of small worms and crustacean-like animals have been documented living just above or within the anoxic layer. They survive by positioning themselves carefully at the boundary where oxygen becomes low but not entirely absent, or by hosting symbiotic microorganisms that help process the chemical compounds around them. In some blue holes, researchers have found simple animals almost fully immersed in sulfide-rich water, relying on internal biochemistry that approaches the tolerance limits of multicellular life. These discoveries are recent and continue to shift scientific understanding of what life can tolerate. The stillness here feels different from the stillness above. Up near the surface, quietness came from a lack of motion. Here, quietness comes from a lack of recognizable life. The occasional drifting particle is organic, but not in the way you expect. Most of what's suspended in this water is microbial biomass, dead cells, or partial metabolic byproducts released from deeper mats. There are no schools of fish weaving through the water, no flashes of colour or quick shifts in movement. Instead, the space holds a deliberate calm, shaped by chemical rhythms rather than biological ones. If you move your light across the water column, the beam spreads softly, diffused by suspended organisms and dissolved compounds. The deeper environment changes from darkness to a kind of muted haze. The light doesn't travel far because hydrogen sulfide absorbs illumination differently from oxygen-rich water. It's not a dramatic absorption, but it contributes to the sense that the water itself has become thicker, even though it hasn't. The perception comes from visual damping rather than physical resistance. If you imagine placing your hand directly in the water and scooping it upward, It wouldn't feel different in temperature from the layer above, but your mind would register the invisible differences. You're in a zone that rejects your own metabolic rules. If you stayed here without equipment, your body would have no means to generate energy. Your cells would be unable to complete the biochemical processes that keep you alive. Yet the organisms around you experience none of that limitation. They evolved before oxygen became widespread, and their descendants have adapted to fill niche environments that mimic those ancient conditions. These organisms represent a timeline stretched backward millions, even billions of years. They don't belong to the modern chapter of marine evolution. They belong to the early chapters, when Earth's oceans were chemically rich but oxygen poor. They reveal a world where anaerobic metabolic strategies shaped the pace of evolution long before photosynthesis began enriching the atmosphere. Blue holes become time capsules not because they preserve fossils, but because they preserve environments compatible with these ancient life forms. If you hover at this depth for a moment and turn your light toward the limestone walls, you might notice faint streaks that appear almost powdery. These streaks contain layers of microbial mat that thrive on extremely narrow chemical gradients. Each layer represents a specific metabolic group using a particular electron source, an electron acceptor. The structure looks simple, but it represents complex ecosystem engineering. These organisms do not live randomly. They live in defined bands because each band corresponds to the exact chemical balance they require. This stratification resembles the layered structures found in ancient stromatolites, except here the layers are microscopic and embedded into the walls rather than forming large external mounds. Still, the principle is similar. Ancient life relied on gradients to structure communities. Here, gradients still rule. As you continue deeper, the water transitions further. The concentration of hydrogen sulfide reaches levels lethal to most marine life. The smell, again, would be overpowering if exposed to air, but underwater the effect is dissolved, and chemical rather than olfactory. This layer often appears slightly cloudy due to suspended microbial biomass. The organisms metabolizing sulfur compounds generate byproducts that feed other microbial groups nearby. Even without fish or plants, the system maintains a web of interdependent life. This is where the term breathing differently becomes more than a phrase. These organisms don't breathe oxygen. They negotiate chemical energy from compounds that surface life would avoid. Their world doesn't revolve around gas exchange. It revolves around electron flow in a chemical landscape shaped by the surrounding limestone and trapped water. This zone, despite its harsh chemistry, supports high microbial productivity. The mats grow rapidly. The biomass cycles continuously. If you looked at the metabolic output in terms of biochemistry, rather than numbers of animals, this layer could compete with surface ecosystems in intensity. It's just expressed through chemistry rather than movement or colour. Nothing here wastes energy. Motion is slow. Growth is deliberate. Survival depends on efficiency, not intelligence or speed. Every organism that persists in this zone does so by balancing the influx and outflow of chemicals. The entire ecosystem performs the slow balancing act that once shaped early Earth. Even though this environment feels quiet and empty, it's one of the most productive microbial zones in any marine structure. Researchers studying these systems often find that the organisms here cycle nutrients at rates surprisingly high for such visually barren environments. It's only barren to human eyes. At the microbial scale, it's busy. The deeper layers beyond this point hold their own surprises, including pockets where rare or unique species appear in isolated niches. But this zone marked by the absence of oxygen is where the blue hole begins revealing its deeper identity. It's not a place where life fails. It's a place where life revisits an older rulebook, one that predates most of the organisms familiar to us today. And as we continue, the chemical landscape tightens its grip. The boundary we crossed wasn't the last one. Farther down, the water changes again, and the organisms that thrive there shape another step in the evolution of life inside these deep, secluded spaces. By the time you've settled fully into the oxygen-free zone, it becomes clear that the organisms thriving here are not survivors in the simple sense. They aren't clinging to the edges of habitability or scraping by on minimal resources. They are shaping the environment around them actively, stabilizing it, manipulating it, and maintaining it in ways that seem almost deliberate. They are not just inhabitants, they are architects of the deep, working through chemical processes so old they predate not just human understanding, but the majority of life we normally think of when imagining the ocean. These microbial kingdoms operate according to rules that don't require sunlight, rely on chemical currencies foreign to most organisms, and contribute to the structure of the blue hole in ways you can actually see if you know what to look for. As you hover in the dim haze and let your eyes adjust to the muted light, faint patterns begin to emerge on the walls and in the water column. What looked like irregular discolorations a moment ago now resolve into networks of microscopic activity. Entire mats of bacteria spread across the limestone like living carpets, though nothing about them resembles the greenery found in sunlit parts of the sea. They don't bloom in bright pigments or sway with currents. Instead, their presence forms a textured coating across rock, sometimes smooth, sometimes layered, sometimes composed of delicate web-like filaments that extend outward in barely perceptible motions. These structures aren't decorative. They serve as complex metabolic interfaces between different chemical gradients. A curious thing about microbial communities in places like this is how collaborative they are. On the surface, ecosystems are defined by food webs built through direct predation or competition. Down here, energy flows through chemistry rather than hunting. Rather than fighting for resources, microbes tend to organize into cooperative assemblages. One group releases a byproduct that another group uses. A third group may rely on the waste of the first two. The entire community functions like a biochemical factory line, each section performing a specific reaction that keeps the system balanced. To consider them individually is to miss the point. These organisms are not isolated workers. They are parts of a metabolic circuit. For example, certain bacteria oxidize hydrogen sulfide, converting it into sulfate in reactions that release energy. Other bacteria rely on that sulfate as an electron acceptor to continue entirely different metabolic processes. Still others use the carbon compounds excreted by their neighbours to build biomass. The microbial mats that line the walls are organised around these overlapping needs, stacking layers of organisms in precise arrangements that maximise efficiency. The architecture isn't accidental. It forms wherever the chemical gradients are optimal, meaning the mats become visible maps of invisible chemistry. The water in this zone is often dense with tiny particles that aren't sediment, but clusters of microorganisms drifting freely in the column. Some are actively swimming, though at a scale too small for your eyes to detect. Others disperse through Brownian motion or slight water movements. Each particle represents a cell or colony of cells, performing reactions that would be incompatible with life in oxygen-rich water. Their presence fills the space with constant microscopic activity that never becomes obvious until you shine a light on it. Even then, the activity reveals itself not through motion, but through the faint cloudiness that seems to thicken and thin as you pass through different depths. One of the most striking features in these microbial kingdoms is the existence of distinct layers. While fish and larger animals occupy broad zones, microbes sort themselves using precision. A layer only a few feet thick might host entirely different metabolic processes from the layer above or below. These shifts are determined by how the chemicals diffuse through the water. A small change in the availability of sulfide or nitrate can create an entirely new neighbourhood of microorganisms. Structures form spontaneously as microbial communities grow in areas that suit them, and in doing so they reinforce the chemical boundaries that define these layers. Some blue holes contain a clearly visible band known as the white cloud, a region where microbial mats release tiny sulfur granules that scatter light in distinctive ways. It can appear as a milky band stretching horizontally through the water column. Divers often describe the experience of passing through it as similar to drifting into fog. This cloud isn't uniform, it thickens in some places and thins in others, depending on how the microorganisms cluster and how much byproduct they generate. The cloud doesn't move with waves or currents because the surrounding water remains so still. It simply exists in a fixed layer, marking a sharp division between habitable zones. Below the white cloud, the microbial populations change again. Here, the water may contain higher concentrations of reduced sulfur compounds, and only the organisms adapted to these extremes can persist. Many of these bacteria rely on metabolic pathways present on Earth long before the rise of oxygenic photosynthesis. These pathways, documented in ancient rocks dating back billions of years, likely supported the earliest life forms on the planet. Seeing them active today isn't just a matter of curiosity, it's a reminder that blue holes are windows into Earth's microbial past. They reveal how life once operated when oxygen was scarce or non-existent, and how intricate biological systems thrived despite environmental conditions that would kill most modern organisms instantly. If you drift slowly toward one of the walls, the microbial mats become easier to examine. A soft beam of light reveals layers of texture on the limestone. Some sections look like thin films spread across the rock, barely noticeable unless illuminated. Others form thicker, spongier-looking patches that can ripple slightly when water pressure shifts. These mats can be surprisingly resilient. They anchor themselves to the stone using secreted polymers that act like biological glue, allowing them to withstand gentle disturbances without dislodging. If a diver brushes by too closely, the mats may sway but rarely detach. They rebuild themselves rapidly even if partially disturbed. In some blue holes, entire formations called streamers develop, resembling strands of pale fibre dangling from the ceiling or walls. These streamers consist of long filamentous bacteria that extend outward to occupy pockets rich in dissolved sulfur. The appearance is almost ghostly, though the effect is more structural than aesthetic. These filaments allow the bacteria to bridge areas of different chemical composition, ensuring that they remain anchored in zones that maximize their energy gain. Streamers can grow to notable lengths and cluster in ways that appear intentional, though they form simply through growth patterns guided by chemical exposure. The deeper communities reorganize themselves again as chemical gradients steepen. Here, the water becomes increasingly dominated by hydrogen sulfide. Oxygen is entirely absent. The organisms metabolizing sulfur compounds dominate the scene, turning the environment into a hotspot of anaerobic metabolism. They feed on sulfur in cycles so efficient that the water chemistry remains stable over long periods. Unlike surface ecosystems that depend on sunlight and fluctuating nutrient inputs, these microbial kingdoms rely only on the steady chemical interactions between rock, water, and biological activity. The walls of the blue hole act like massive reaction chambers. Water trapped within the structure reacts with limestone, releasing calcium and altering pH levels. These changes influence which microbes can colonize which parts of the wall. Some thrive in slightly acidic pockets, others prefer alkaline niches. The diversity within these microbial mats is remarkable, even though the environment appears monotonous to the naked eye. Under a microscope, it becomes clear that the mats contain thousands of species, each occupying a specific role in the chemical network. One of the most fascinating features uncovered in certain blue holes is the presence of layered microbial communities that resemble miniature versions of stromatolites. Stromatolites are ancient biological structures formed by the layering of microbial mats over long periods. In blue holes, similar layering occurs as different microbial communities respond to slow shifts in available compounds. Over time, these layers accumulate subtle structural features in the rock, though the effect is far smaller and more fragile than the ancient formations found in shallow marine areas. These microbial kingdoms don't simply respond to their environment, they create it. By consuming hydrogen sulfide, producing sulfate, and releasing other compounds, they continually modify the chemical conditions around them. These changes, in turn, influence which microbial groups can thrive in adjacent zones. It's a constant feedback loop where life and environment shape each other. In many ways, the structure of the blue hole as you experience it, the layering, the cloudiness, the chemical gradients, is maintained not just by geological constraints, but by the ongoing work of invisible architects. Scientists studying these environments often take water samples from different depths to analyse microbial composition. What they find is surprising even to those familiar with extreme environments. The microbial diversity rivals that of surface ecosystems, even though nearly all of the organisms rely on anaerobic metabolism. Some sequences collected from certain blue holes don't match any known microbes. These organisms belong to lineages that likely branched off early in Earth's history and have remained isolated in chemical refuges like these deep pits. Discovering them is not just an exercise in exploration. It broadens our understanding of the resilience of life and the variety of strategies evolution can produce. If you pause and imagine the microbial activity happening around you, the scale becomes almost overwhelming. Billions of cells complete metabolic reactions every second. Entire mats shift slightly as chemical concentrations change subtly. Streamers pulse with new growth as sulfur diffuses through the water. Everything here is busy, but none of it moves the way animals move. None of it reveals its activity through noise or motion. The productivity is quiet, constant, and invisible, unless viewed with the proper tools. This quiet productivity is what keeps the deeper layers of the blue hole stable. Without the microbial consumption of hydrogen sulfide in the upper parts of the anoxic zone, sulfide levels near the transition zone would be much higher. Without the metabolic breakdown of organic matter, nutrients would accumulate in forms that destabilize the water chemistry. These microorganisms control the flow of matter and energy within this environment, maintaining balance in a place that should, by most logic, be unstable. The deeper regions hold additional communities with even more specialized metabolic strategies. Some rely on methane oxidation, others engage in iron reduction. A few rare groups use nitrogen compounds in complex ways. These organisms don't compete directly. They occupy distinct microenvironments defined by rock texture, mineral composition, and the slow seep of dissolved gases from below. Blue holes become entire ecosystems not because of plant and animal diversity, but because of microbial specialization that transforms every centimetre of water and rock into potential habitat. As you hover in this space, it becomes clear that what appears empty is actually dense with life. The stillness doesn't imply absence, it implies order. The water, the mats, the streamers, the drifting particles, all of it functions as a vast interconnected system that has been refining itself for thousands of years. And farther below, the chemistry sharpens again, creating another domain where even these hardy organisms begin to give way to those adapted to the deepest, darkest conditions the blue hole offers. Once you've spent enough time among the microbial layers and begun to understand how thoroughly life has adapted to absence rather than abundance, it becomes even more surprising to realize that not everything thriving in these depths is small or passive. In environments where oxygen vanishes, where hydrogen sulfide fills the water column, and where nothing resembling sunlight penetrates the haze, you might expect silence to mean emptiness. But the stillness here is deceptive. Not all life in the pit is microscopic. Some of it moves with purpose, scans its surroundings carefully, and hunts with patience that only a place like this could teach. Predators exist in this strange pocket of the sea, though none resemble the sharp-jawed hunters from coral reefs or open-water ecosystems. These predators are unexpected, often underestimated, and in some cases barely studied, because they live in niches so isolated that most marine scientists rarely encounter them. When you drift downward past the densest layers of microbial haze, the water clears slightly in a way that feels counterintuitive. You might think the deeper regions grow more turbid, but instead the heavy microbial production stays anchored to the chemical boundary above. Below that point, organisms shift strategies. The mats clinging to the walls have grown thicker. The free-floating cloud has thinned. The water appears emptier. This visual emptiness creates a moment where you might think nothing exists here except the mats themselves and the dissolved chemicals that fuel them. But this zone, shaped by near total darkness and chemical gradients, hosts its own food web built on quiet predation. The first sign that something larger than bacteria lives here is movement, slow at first, faint enough to escape notice until you commit to watching carefully. Tiny crustaceans drift in the dim light. These are not the bright, fast-moving amphipods you might find near coral outcrops. They're pale, sometimes nearly transparent, with reduced pigmentation and elongated appendages that help them sense chemical cues rather than relying on vision. Their movements are cautious and deliberate. They occupy the narrow band of water where the conditions aren't yet fully toxic, but have already thinned out oxygen to dangerously low levels. They float in slow arcs, pausing at seemingly random intervals. A diver might mistake them for debris if they weren't moving independently. These small crustaceans play a crucial role as prey for the predators of the pit. Their survival depends on efficiency. Instead of navigating by sight, they rely on the faintest pressure changes and chemical signals. They feed on drifting organic particles that fall from the microbial layers above or accumulate from the decomposition of organisms deeper down. Their strategy is simply to move as little as possible, conserving energy in a place where unpredictability offers no advantage. If you remain still long enough, a different kind of motion appears, almost like the shadow of a shadow. Some blue holes host species of shrimp that have adapted to the unique conditions here. These shrimp lack the bright colours associated with their shallow water relatives. Instead, they appear as pale outlines with oversized sensory structures. Their antennae sweep the water in slow, deliberate arcs. They feed on both microbial mats and the tiny drifting organisms that share this depth, and on rare occasions they hunt each other. Their world is defined not by territory, but by probability, because prey in this zone is sparse and patchy. These shrimp move in slow steps, pausing frequently, as if recalculating their position using chemical gradients rather than visual cues. It might seem strange to call these organisms predators given their size and sluggish movements, but predation at this depth looks nothing like the rapid chases that dominate surface ecosystems. Down here, a successful hunter is one that conserves energy. The predators that thrive in these conditions aren't fast, they are patient, they are sensitive, and they are opportunistic. A crustacean that drifts a little too close, fails to detect a subtle pressure wave, or moves at the wrong moment can be caught in a brief burst of movement that comes and goes before your eyes are fully aware of what happened. In deeper pockets along the walls, simple worms inhabit crevices filled with rotting organic material. These organisms are not hunters in the traditional sense, but they do consume small prey when the opportunity arises. They extract nutrients from decaying matter and occasionally catch drifting amphipods or smaller worms that wander into their narrow feeding range. Their bodies are slender and flexible, allowing them to slip into cracks where more agile animals can't follow. While they don't roam the water column actively, they represent another link in the web of predation, using the environment around them to collect food without expending much effort. As you move farther into the darkness, the predators become even more surprising. Some blue holes contain species of fish that appear only in the deepest areas of the pit, emerging from overhangs or undercuts carved into the limestone. These fish often show drastic adaptations: reduced eyes, pale or translucent skin, elongated fins, and altered swim patterns designed for energy conservation. They do not rely on bursts of speed. Instead, they hover motionlessly until prey drifts near enough for a single decisive strike. They often feed at the boundaries where chemical gradients shift abruptly, because prey species tend to gather at the edges of metabolic zones, where food particles accumulate, and where visibility, even in the darkness, is slightly improved due to the thinning microbial cloud. One of the most fascinating things about these deep adapted fish is that they don't follow the behaviours typical of reef fish. They don't patrol territories, form schools, or engage in displays. They move quietly and infrequently. Their muscles, and the energy they burn, must be managed with extreme care. In an environment where oxygen is absent or nearly so, even simple actions require careful control. These fish rely heavily on anaerobic metabolic pathways, which limit the burst speed and endurance they can achieve. As a result, they compensate with stealth. They feed by waiting. They conserve every calorie. They attack only when necessary. If you shine light toward the walls, you may see small openings leading into submerged cave systems branching off from the main shaft. The entrances to these tunnels often host concentrated microbial mats and small drifting particles, drawing prey species that rely on these resources. Hidden within these openings, certain fish and crustaceans wait silently. They use the geological structure of the blue hole as part of their hunting strategy, taking advantage of the steady flow of organic matter that becomes trapped in the architecture of the rock. There is a kind of stillness to these predators that makes them difficult to detect. Unlike the recognizable shapes of shallow water species, their bodies blend into the background. Their outlines soften in the dim light. You don't see them until they move. Even then, the motion is so quick and economical that it almost seems like a glitch in your perception rather than a biological strike. Many divers describe the moment when one of these predators flicks its tail or snaps at drifting prey as more startling than encounters with large, fast animals in the open ocean. It's not the speed that surprises them. It's the sudden presence of something they hadn't noticed in a space they thought they'd fully scanned. The deeper you go, the more apparent it becomes that predation here is shaped by scarcity. In more abundant ecosystems, predators and prey maintain dynamic relationships that shift daily with tides, currents, and nutrient availability. Down here, the movements are slower not just because metabolism demands it, but because the availability of food is unpredictable. A predator may wait hours or even days for a suitable prey item to pass close enough for a strike. A single successful feeding event can sustain some of these organisms for long periods. Hungry periods are normal. A feast does not spark a frenzy. It simply resets the cycle. Another type of predator in these depths is a category many divers forget to consider: microbial predators. Though invisible to the naked eye, some bacteria in these layers consume other bacteria. They have evolved ways to invade neighbouring cells or latch onto them and siphon nutrients. This type of predation is vastly different from anything seen in larger creatures, but at this depth, microbial predation is essential. It shapes population dynamics. It prevents explosive growth of a single species. It sustains the delicate balance of chemical reactions that define the entire system. In some blue holes, bacterial predators outnumber larger hunters by countless orders of magnitude. Yet their presence remains unnoticed, unless revealed through careful sampling and microscopic analysis. The walls of the pit also host microfauna that engage in a different kind of predation: filter feeding. While filter feeders are often associated with oxygen-rich environments and fast currents, some tiny organisms here have adapted their filtering structures to capture microbial biomass and dissolved organic molecules in oxygen-poor conditions. They feed on whatever drifts by, whether living or dead, playing a role similar to scavengers in other ecosystems. Their feeding behaviour may not resemble hunting in the traditional sense, but in an environment where nutrients are sparse, their ability to extract value from whatever passes them places them squarely within the category of opportunistic predators. The absence of oxygen also pushes evolution in unexpected directions. Some organisms develop symbiotic relationships with sulfur-oxidizing bacteria, which help them tolerate toxic conditions and process nutrients unavailable to other species. These partnerships blur the line between predator and prey. In some cases, the host organism becomes a mobile environment for the microbes, carrying them into pockets rich in hydrogen sulfide. The bacteria perform the complex chemical reactions, releasing organic compounds the host can absorb. The host, in return, provides movement and exposure to new chemical gradients. Neither can survive alone in this layer, but together they form a hybrid predator, exploiting the chemical resources around them with surprising efficiency. Occasionally, explorers documenting deep blue holes have observed larger creatures passing through these layers briefly. Some species of shark glide along the perimeter of the pit, but rarely descend into the fully anoxic zones. Even these temporary visitors influence the predator dynamics of the upper layers, though they remain only for short intervals. The real long-term hunters reside deeper, fully adapted to the chemical and sensory challenges of the environment. In the lowest regions where predation still occurs, food sources shift again. Organic matter descending from the upper layers becomes the most reliable resource. Some organisms feed directly on the microbial mats that line the walls. Others graze on decomposing remains of animals that died elsewhere in the pit. Because decomposition happens differently in low-oxygen environments, remains persist longer, allowing diverse organisms to extract nutrients slowly over time. This process creates small but stable food reservoirs that support entire communities of scavengers and micropredators. The hunting behaviours in these layers are subtle. Instead of bursts of speed or dramatic displays, the predators communicate through minuscule displacements of water, chemical signals and momentary shifts in position. If you were to pause and watch closely, you might see a crustacean drifting one moment and lunging the next, or a worm emerging from a crevice to seize a particle that strayed too close, or a pale fish adjusting its posture by fractions of an inch as it detects faint pressure changes from potential prey above. What these predators share is a lifestyle shaped entirely by constraint. The chemical landscape determines where they can move, what they can eat, and how their bodies produce energy. Unlike predators at the surface who rely on vision, speed, and muscle, the organisms here rely on chemical senses, patience, and conservation. They know immobility is often the best strategy. They know that movement must be precise. They know the value of stillness in a place where survival depends on tight energy budgets. The remarkable thing is not that these predators exist despite the harshness of the environment. The remarkable thing is how well they've adapted to it. They are not weakened versions of their shallow water relatives. They are specialists. Their bodies and behaviours are honed by generations of evolution to function in isolation, in toxicity, in darkness. They represent a unique snapshot of how life moulds itself around the constraints of chemistry and still finds ways to hunt. As you continue downward from this zone, leaving behind the small predators and entering regions where the environment shifts again, the blue hole begins revealing yet another layer of complexity, shaped not by motion or biology, but by the chemistry that becomes increasingly extreme the deeper you go. As you move deeper into the blue hole and leave behind the last traces of predatory life that managed to hunt in these difficult conditions, the water around you begins to change in ways that no longer resemble even the most extreme environments of the open ocean. The shift is gradual at first, almost gentle, then unmistakable. The clarity you briefly saw in the deeper microbial zone starts to fade into something thicker and more opaque. Your light no longer stretches outward with predictable reach. It fades more quickly, absorbed by compounds that aren't normally found in high concentrations in seawater. This is the point where the chemistry of the pit takes over entirely. The biological activity you witnessed above is still present in massive quantities, but now it's supported and shaped by a chemical landscape that almost seems designed to keep outsiders away. It doesn't take long before the presence of hydrogen sulfide becomes undeniable. You can't smell it underwater, but you can see its effect in the way the beam of your light loses intensity and diffuses through the water as if passing through smoke. The particles drifting past you are not silt or sand. They are microbially produced compounds suspended throughout the water column, forming a natural veil that marks the beginning of a chemically distinct world. Hydrogen sulfide is highly toxic to most organisms. It shuts down cellular respiration by interfering with essential enzymes and blocking oxygen transport within cells. In a fully oxygenated environment, it would disperse quickly, But here, where mixing is minimal and oxygen is absent, it accumulates steadily, creating layers that remain isolated for decades or centuries. If you visualize the water column from above, the blue hole resembles a layered drink in a glass where different liquids separate because of density differences. Warm, oxygen-rich water sits at the top. Beneath it lies cooler, increasingly oxygen-poor water. Then the anoxic layer begins, and finally you reach the hydrogen sulfide-rich water. These layers rarely mix. When they do, the disturbance might remain visible for days as the chemistry struggles to return to equilibrium. The structure of the blue hole acts like a natural container, preventing strong currents from pulling deep water upward or pushing surface water down. The result is a stratified chemical system that exists nowhere else in the marine environment with such clarity and consistency. If you extend your hand into this deeper water, again, only in imagination, because such a thing isn't safe, the sensation wouldn't reveal anything unusual. Temperature shifts are mild. Density differences aren't enough for the human body to detect. What makes this water poisonous is invisible. The danger lies in the molecules diffused through it. It's the kind of threat that does nothing to your senses until it's already inside your bloodstream. This mismatch between perception and danger is what gives the deeper zones an uncanny feel. You're surrounded by water that looks calm and harmless, but is fundamentally incompatible with the biological machinery keeping you alive. For the microorganisms that dominate this layer, the chemistry is not an obstacle, but a resource. Hydrogen sulfide, lethal to most organisms, provides ample energy for microbes adapted to metabolize it. They extract electrons from sulfide in reactions that generate energy and release sulfate back into the water. This metabolic pattern is the mirror image of processes used by organisms that rely on oxygen. To the bacteria here, this chemical soup is not only tolerable, but advantageous. It allows them to dominate a region without competition from oxygen-breathing life forms. Some bacteria in this zone don't rely on sulfur at all. Instead, they may metabolize methane or iron compounds, diffusing upward from deeper sediments. The variety of metabolic pathways present in these waters is astonishing. Each one follows a biochemical strategy that diverged from the main evolutionary trajectory millions of years ago. These microorganisms represent alternative solutions to the problem of energy production, shaped by environmental conditions that more closely resemble early Earth than the modern ocean. If you were to lower scientific instruments into the pit, the changes in water chemistry would become clear long before you reach the bottom. Hydrogen sulfide concentrations rise steadily. pH levels shift. Dissolved inorganic carbon increases. Certain metals, normally present only in trace amounts, become measurable because the reducing conditions cause them to dissolve from rock surfaces. The water becomes chemically reducing rather than oxidizing, meaning chemical reactions proceed in the opposite direction from those typical in oxygen-rich environments. For many scientists, observing these chemical processes in action is like seeing a living experiment in planetary chemistry. One of the most distinctive visual features created by this chemistry is the developing boundary, where hydrogen sulfide concentration suddenly increases. It often appears as a dense, pale layer that floats horizontally through the water column. When divers descend into it, everything above this layer becomes tinted by its presence. Light struggles to penetrate it, casting a muted, chalky glow across whatever lies beyond. Even the walls of the pit vanish into a backdrop that feels more like a closed room than an open underwater space. This layer acts as a barrier in more than a physical sense. Many animals refuse to cross it. Even species that occasionally feed near its upper boundary retreat long before entering the chemically charged water. For larger organisms with developed respiratory systems, immersion in this layer would be lethal within minutes. The hydrogen sulfide binds to respiratory enzymes rapidly, shutting down the pathways that convert oxygen to usable energy. In humans and most marine animals, this leads to rapid unconsciousness followed by death. The only reason divers can safely pass through this layer is because they carry their own air supply. Even then, extended exposure to high hydrogen sulfide concentrations can corrode equipment and irritate exposed skin or eyes, depending on its intensity. The deeper you descend, the more the water chemistry becomes alien compared to the typical ocean. Dissolved oxygen drops to zero. Hydrogen sulfide continues to rise. Ammonium and other reduced nitrogen compounds increase as organic matter decomposes without oxygen. Iron, normally present in limited forms in seawater, becomes soluble in higher concentrations. Manganese may also become more mobile. These changes form an environment where metabolic strategies follow anaerobic rules entirely. If you brought a sample of this water to the surface and exposed it to air, the chemistry would change rapidly. Hydrogen sulfide would oxidize, metals would precipitate out, the colour might shift slightly. But down here, the water has remained in a consistent chemical state for years or decades, untouched by external forces. One of the more surprising features of this chemical landscape is that it preserves organic matter extremely well. In oxygen-rich environments, dead organisms decompose rapidly due to biological and chemical oxidation. Here, decomposition slows dramatically. Organic remains can persist much longer, providing a slow but steady supply of nutrients for organisms adapted to make use of them. In many blue holes, layers of ancient organic sediments have accumulated at the bottom, protected from decomposition by the toxic chemistry above. These sediments serve as historical records, storing information about climate conditions, microbial communities, and environmental changes going back thousands of years. The limestone walls also reflect this chemical isolation. Over time, exposure to hydrogen sulfide and other reduced compounds alters the minerals in the rock. Some areas dissolve more quickly, forming pits and pockets where microbial mats gather. Other areas harden as minerals precipitate out of solution. The physical structure of the blue hole is constantly shaped by biochemical interactions between rock, water, and microbial activity. These changes occur slowly, too slowly to observe in a single dive, but over centuries the combined effect reshapes the architecture of the pit. It might seem surprising that certain multicellular organisms can survive in such chemically extreme waters, yet some species persist by exploiting microhabitats with slightly milder conditions. These creatures rarely enter the densest sulfide layer, and instead position themselves along the edges where chemical interactions are less extreme. They rely on metabolic flexibility or symbiotic relationships with bacteria that neutralize or process toxic compounds. These organisms don't thrive in the poisonous zone the way microbes do. They survive because they've adapted not to interact with the chemical environment directly, but to manage its effects indirectly through biology. The deeper waters also contain pockets where gases accumulate. These pockets form in crevices or inverted sections of the cave wall, where hydrogen, sulfide and methane gather before dissolving into the surrounding water. If disturbed, these pockets release clouds of gas that alter the local chemistry temporarily. Scientists have observed cases where these disturbances create small but visible plumes of changed water composition that drift upward slowly. The release doesn't pose immediate danger to a diver with equipment, but it highlights how unstable these deeper layers can be if disrupted. One of the more unusual aspects of this chemical environment is how sharply defined the boundaries can be. While surface waters mix continuously, the boundaries in a blue hole can remain stable to a degree that seems more appropriate for laboratory solutions than natural waters. A shift of just a few inches can take you from water with low sulfide concentration into water rich with it. This precision results from the lack of currents and the structure of the pit, which prevents even tidal mixing. Where ocean water turns over quickly, blue hole water remains layered and locked in place. The layers also act as light filters. As your light passes downward, the hydrogen sulfide absorbs certain wavelengths more than others. This creates a muted, almost monochromatic appearance. The deeper you go, the more your surroundings lose contrast. Objects seem to fade into the background even when illuminated. The walls might appear closer or farther than they really are because the particles in the water scatter light in unpredictable ways. Depth perception becomes unreliable, even for experienced divers. Everything looks slightly flattened, as though the environment were compressing its details. Understanding this chemistry has implications far beyond blue holes themselves. Scientists use these environments as analogues for early Earth oceans before oxygen became abundant. The chemical conditions down here mirror those of ancient seas where early microbial life dominated long before multicellular organisms emerged. Studying the microbial communities and chemical reactions in blue holes provides insights into how life might have evolved on Earth billions of years ago. It also helps researchers imagine what kinds of environments might support life on other planets or moons with oceans lacking oxygen, such as Europa or Enceladus. Even though the deeper layers seem harsh, they support a coherent, functioning ecosystem. Microorganisms feed on sulfur compounds. Other organisms feed on them. Organic matter slowly decomposes and fuels additional microbial activity. The system is isolated but not stagnant. It's dynamic in a way that doesn't require movement. The chemistry drives the biology, and the biology drives the chemistry. It's an elegant, self-sustaining cycle that relies on poisonous compounds to maintain stability. As you continue downward into the deeper portions of the pit, the water grows darker still, not from the absence of light, but from the increasing density of dissolved compounds. You've passed through layers shaped by biology, and entered layers shaped almost entirely by chemistry. And deeper still, the environment continues to shift in ways that reveal how life adapts when even poisonous waters become the foundation of survival. Once you reach a depth where the chemistry settles into its strongest patterns, and the water begins to feel more like a preserved solution than a living environment, something becomes clear that wasn't obvious in the layers above. The deeper zones of a blue hole are not only shaped by the life that survives there, they also hold on to the remains of life that came long before. What settles in these depths doesn't behave the way it does in the open ocean. The lack of oxygen slows decay to a pace that seems almost frozen. Organic matter doesn't vanish quickly. Sediments rest where they fall. Chemical reactions follow slower paths. This creates a natural vault where environmental records accumulate layer by layer with minimal disturbance. Because of this, blue holes function like ancient archives, places where the past lingers in forms the surface world has long forgotten. As you glide deeper into these quiet sediments, the sense of entering a preserved timeline becomes stronger. The water around you no longer shifts in colour or clarity, the way it did in the upper layers. Down here, everything feels still, not because there is no movement, but because the environment doesn't allow much change. What reaches the bottom eventually becomes part of a layered history. The sediments rest in thin sheets that reveal periods of drought, floods, storms, and tides from centuries ago. Each layer captures a different moment in Earth's story, sealed away by the same chemistry that makes the blue hole toxic to most forms of life. If you imagine scooping a handful of this sediment, you'd be holding a compressed timeline. It would contain fragments of ancient plant material washed in from shorelines that may not even exist anymore. It would contain shells of microorganisms long dead. It would contain particles from storms so old their weather patterns can only be reconstructed through paleoclimate studies. In some blue holes on land, particularly in places like the Bahamas, the sediments preserve entire skeletons of extinct animals, including species that roamed during ice ages. While underwater blue holes don't often contain such large remains, they still preserve a record of ecological and geological events that would otherwise be lost. The deeper you go, the more profound this preservation becomes. In an oxygen-rich environment, bacteria and chemical oxidation break down organic material rapidly. Bones dissolve, wood decays, textures disappear. But in a low-oxygen or anoxic system, decay slows to the point that organic matter persists far longer than it otherwise would. The bottom of a blue hole becomes a compressed library of remains that read like entries in a logbook. Scientists studying these sediments can trace the appearance and disappearance of species, changes in water chemistry, fluctuations in rainfall, and even human influence extending back thousands of years. The limestone walls also serve as a geological record. Dripstone structures formed when the cave was dry remain preserved underwater. Their shapes reveal periods when sea levels were far lower and the cave system was exposed to air. Some of these structures resemble delicate curtains, stalactites, or other cave formations. Their presence confirms that the blue hole formed when the region experienced conditions very different from the present day. Sea levels rise and fall over geological timescales. What is underwater today may have been a dry chamber tens of thousands of years ago. The walls hold the marks of those transitions. Each groove and ridge records a period of dripping water, airflow, mineral deposition, or collapse. These structures aren't altered much by the modern environment. The anoxic layers protect them from rapid dissolution. While chemical interactions reshape some parts of the walls, the deepest limestone retains features carved when early humans were just beginning to spread across continents. In this sense, blue holes bridge the gap between Earth's geological memory and its biological memory. They contain evidence from both. As you continue inspecting this deeper region, the sediments become thicker and darker. The composition changes from granular material to fine organic muds that cling loosely to the floor. Scientists often extract long sediment cores from these layers. Each core becomes a column of Earth's forgotten history, sealed, uninterrupted, and easy to analyze with modern techniques. These cores reveal pollen from plants that once grew near the shore, fragments of charcoal from ancient wildfires, and particles carried by winds during storms that humans never recorded. This is why blue holes are often used as climate repositories. They capture environmental events without the interruptions caused by currents or burrowing animals. One of the most intriguing aspects of this archive is how well it separates different eras. Because the water column rarely mixes, the sediments settle gently and remain undisturbed. Layering remains intact. What lies at 20 centimeters depth corresponds to 1 century. 40 centimeters might represent 2 centuries. Depending on the rate of accumulation, the deepest layers could contain records from thousands of years ago. In some blue holes, researchers have found sediments dating back more than 10,000 years, preserved so cleanly that seasonal patterns and individual storm events can be identified. This means blue holes do more than preserve history. They offer clarity. They filter out distortions caused by biological and physical disturbances common in other environments. The absence of burrowing organisms in anoxic zones keeps the layers intact. The absence of strong currents prevents the sediments from being swept away or redistributed. The poisonous chemistry slows microbial activity, allowing structures and particles to remain preserved without rapid decomposition. All these factors combine to form an environment where the Earth's memory accumulates naturally. In addition to sediments, blue holes on land and underwater capture biological remains that would otherwise degrade quickly. Some contain the bones of birds swept in by storms. Others contain small crustaceans or fish that died deeper in the pit and fell to the bottom. In certain blue holes connected to larger cave systems, fossils of extinct species have been discovered in extraordinary condition. These remains become valuable tools for understanding how species moved, adapted, or disappeared as the climate shifted. If you imagine what Earth looked like 10,000 years ago, you might picture glaciers, different coastlines, and entirely different communities of plants and animals. Blue holes preserve evidence of those changes. Thin bands of pollen embedded in the sediment map out ancient forests. Layers rich in certain minerals reveal drought periods. Layers darkened by charcoal confirm seasons of intense fire. Shell fragments indicate shifts in salinity or changes in sea level. Every centimetre of sediment becomes a page describing how the environment behaved at a specific moment in time. This ability to preserve such detail makes blue holes valuable for studying sea level rise. Researchers use isotopic analysis and microfossil identification to reconstruct ancient water depths. Because blue holes form in limestone, which retains structural clues from previous water levels, they serve as natural gauges of past ocean movement. The height of mineral deposits on the walls reveals how high or low the water reached at different points in time. These indicators help scientists track changes that influence migration patterns, coastal ecosystems, and climate cycles. The chemical conditions in the deeper layers also preserve certain biological molecules that would otherwise degrade rapidly. Lipids, pigments, and fragments of DNA can survive under anoxic conditions far longer than in oxygenated waters. This allows researchers to extract genetic information from organisms that lived centuries or millennia ago. While the DNA is often fragmented, it can reveal details about species diversity and evolutionary shifts. In many cases, these findings suggest that blue holes harbour lineages of microbes with ancient ancestry, some of which diverged from known branches of life long before humans evolved. Another fascinating aspect of preservation in blue holes is the way certain minerals accumulate around organic material. Hydrogen sulfide interactions with metals can cause mineral precipitation that coats biological remains. This can create protective layers, preserving shapes and structures in ways similar to fossilization, but occurring much more quickly. The mineral coatings protect delicate tissues from immediate decay, allowing scientists to identify structures that would normally vanish within weeks. As you hover above the sediment and take in the quiet stability of this depth, it becomes clear how little the environment changes compared to the surface. The water doesn't churn, the chemical gradients remain fixed, light doesn't shift. The result is a place where time behaves differently. Events that would leave only faint traces elsewhere become permanently recorded here. Even if the upper ocean transforms over centuries, the deepest layers of the blue hole will continue preserving moments from the past as long as the chemical structure remains intact. These conditions extend the significance of blue holes beyond marine biology. They become interdisciplinary archives connecting geology, chemistry, paleontology, anthropology, and climate science. For example, charcoal layers from ancient fires help archaeologists understand when human populations began altering the landscape. Pollen records reveal how ecosystems responded to early agriculture. Sediment chemistry reveals shifts in rainfall. Shell isotopes reveal changes in ocean temperature. The deeper you go into this realm, the more pronounced the sense of preservation becomes. Even microscopic details contribute to the narrative. Fossilized diatoms tell stories of past salinity. Trace metals reveal dust storms. Organic molecules reveal algal blooms from centuries ago. It's not just that blue holes preserve information. They preserve categories of information rarely captured elsewhere. They record the quiet events, the seasonal shifts, the slow migrations of shorelines, the minor changes that add up to major transitions. If you imagine a map showing how coastlines looked thousands of years ago, blue holes serve as anchor points. They show when water levels rose and flooded ancient cave systems. They show when sea levels dropped and left reefs exposed. They show when freshwater lenses sat atop marine water, leaving chemical traces still present today. Each shift leaves a clue somewhere in the rock, the water column, or the sediment. All the while, the environment around you remains motionless. You might expect the pressure at this depth to create a sensation, but the water holds no surprises in that regard. The silence remains uninterrupted. You're suspended in a space where the past hasn't disappeared. It's simply settled. It has taken on physical form in this archive of layers, where every particle finds a resting place and remains part of a continuous record. As you prepare to continue deeper, leaving behind the sediment-heavy layers and approaching regions where darkness becomes more absolute, the environment grows even more stable. The transition from past to present becomes harder to distinguish because the chemical and biological processes continue quietly without erasing what came before. The deeper regions hold additional layers of preservation, not just of Earth's past, but of the ways life adapts when even recorded time seems to slow. The deeper you drift, the more apparent it becomes that light is no longer part of this environment's vocabulary. What began as a gradual dimming in the upper layers now settles into something final. Even the faint scattering produced by your own light appears different. It doesn't illuminate a space the way light does in open water. It pushes only a short distance before dissolving, swallowed by particles, sulfide and water that has forgotten sunlight altogether. The collapse of light begins long before you reach the true bottom of the blue hole, but down here the darkness becomes something with weight. It isn't an absence. It feels built into the structure itself, as if the pit has grown accustomed to a life without illumination. Creatures adapted to this region experience the world through senses that do not rely on vision. Vision here offers little advantage. The wavelengths that travel farthest in seawater disappear as soon as hydrogen sulfide concentrations rise, and by the time you've passed through the densest microbial layers, only the narrowest band of blue can penetrate. Even that disappears long before reaching the deeper recesses. If an organism evolved eyes optimized for this part of the blue hole, they would contribute little to survival. Over generations, natural selection has reduced or eliminated visual structures in many species found here. Some have tiny vestigial eyes, not functional in any meaningful way but retained because evolution doesn't erase features instantly. Others lack visible eyes altogether. Their bodies show smooth surfaces where eyes would normally be, as if the architecture of sight simply never interested them. One of the most fascinating aspects of this adaptation is how consistently evolution moves toward the same solution when faced with eternal darkness. In caves on land, species reduce pigmentation, shrink their eyes, or lose sight entirely. In deep-sea trenches, similar patterns appear. And here, in blue holes, the same process unfolds despite being in a completely different type of environment. Organisms confronted with darkness stop investing energy in producing pigments, maintaining eye structures, or building neural pathways dedicated to visual processing. The energy saved through these reductions becomes crucial in a place where metabolic efficiency means survival. If you hold your light on one of these creatures, the beam reflects almost nothing back. Their bodies lack reflective pigments. They do not shine, they do not flash, they do not create silhouettes. Instead, they slip through the water like shapes carved out of the darkness itself. Even the movement of their bodies remains muted. They do not waste motion. A gentle fin flick replaces a frantic burst. They glide slowly because speed is unnecessary. Prey does not escape quickly. Threats do not appear without warning. The darkness equalizes everything. As you move farther into this realm, the creatures you encounter seem less like animals from the surrounding sea, and more like specialists crafted specifically for this one isolated chamber. Some small fish drift near the walls, their skin pale or translucent. Their bodies reveal internal structures faintly when illuminated. They move with small pulses of their fins, adjusting their positions by inches rather than feet. If a crustacean passes within striking distance, they respond not by lunging forward dramatically, but by making the smallest possible movement. Their jaws snap once, cleanly, and the moment ends. Other creatures use elongated sensory organs to feel their surroundings rather than see them. Long antennae sweep outward. Delicate filaments protrude from their bodies like soft extensions of their senses. These appendages detect chemical gradients, pressure shifts, and movement created by prey or predators. In an environment without light, being able to sense water displacement becomes more valuable than being able to see. Every motion creates a signature that travels through the still water. Larger animals produce distinctive pulses. Smaller drifting organisms create faint disturbances. The creatures living here interpret these signals instinctively, turning toward prey or slipping away from threats with no hesitation. There is a kind of confidence in their movements. They don't test the environment visually. They navigate directly because their sensory systems evolved around the physics of the place. Unlike species in the upper ocean that must respond to constantly shifting currents, light patterns, and predators attacking from multiple angles, the life here exists in a world defined by stability. Water movement is minimal, light is non-existent, chemical gradients remain consistent. In some ways, this stability allows the creatures to narrow their sensory needs. They don't need to see, they only need to sense the changes that matter. Some of the animals living in these dark zones show adaptations resembling those seen in deep cave species. They have elongated bodies, softer exoskeletons, and reduced muscle mass in areas no longer needed. Without the need for rapid directional changes or bursts of speed, muscle groups supporting those movements diminish. These animals become lighter, more flexible, and more energy efficient. Their metabolisms slow. They consume less. They grow over longer periods. The darkness shapes not just their sensory adaptations, but their entire physiology. One adaptation seen commonly in darkness-adapted species is the increase in lateral line sensitivity. In fish, the lateral line is a system of sensory cells that detect vibrations and pressure changes in the water. In the blue hole's deeper layers, the lateral lines of some species become more pronounced. They allow the fish to construct a picture of their surroundings based not on light, but on the shifting pressure field around them. If something moves nearby, the disturbance travels outward, reaching the lateral line long before physical contact. The fish respond immediately, turning toward or away depending on the signature of the movement. In crustaceans, similar adaptations exist in the form of mechanoreceptors, hair-like structures that detect minute water movement. When you see a crustacean pause and hold its antennae forward in these depths, it's not waiting aimlessly. It's collecting detailed information about the world. It senses the direction of drifting particles. It detects faint pulses from microorganisms. It learns something about the shape of the nearby wall or the closeness of an opening. These signals guide predation, mating behavior, and navigation, all without requiring any visual confirmation. As you continue drifting through this dark zone, the silence becomes more pronounced. Earlier, faint noises or movements from the upper water column reached you. Now, nothing travels through the water except your own exhalations and the soft displacement produced by your fins. The creatures around you remain unbothered by your presence as long as you avoid rapid movement. They detect your pressure signature, but they don't treat it the way shallow water species might treat a predator. You are simply another body moving through their environment, producing unfamiliar patterns they evaluate but do not flee from unless you behave unpredictably. Because these species do not rely on vision, they have no instinctual fear response associated with shadows or approaching forms. Instead, their reactions depend entirely on the size, speed, and signature of vibrations. A small, slow movement does not register as a threat. A sharp, sudden motion might send them drifting into deeper recesses. Their calmness becomes part of the environment, reinforcing the sense of a world where actions happen slowly and with purpose. Another key adaptation to life in eternal darkness appears in the metabolic processes of many organisms. Without access to photosynthetically produced food sources, the food web relies on organic matter, drifting downward from upper layers and on the productivity of microbial mats. This limited resource availability favours animals that can slow their metabolisms or enter periods of reduced activity. Many species here drift more than they swim. They position themselves close to the walls where microbial mats accumulate, waiting for small prey to wander near. Predation becomes an exercise in patience, not pursuit. Some animals host symbiotic bacteria that help them process nutrients in the chemically extreme environment. These bacteria may detoxify hydrogen sulfide or assist in breaking down organic material too complex for the host to digest. In return, the host provides mobility or better access to nutrients. This kind of mutualistic relationship reflects how deeply the creatures depend on the chemical environment. Their survival isn't separate from the microbial kingdoms above. It ties directly into the metabolic pathways that define the pit. A few species show adaptations in their circulatory systems that allow them to survive in borderline anoxic conditions. While they cannot function without oxygen entirely, they can tolerate brief exposure or live near the edge of the hydrogen sulfide zone. Their blood contains hemocyanin or hemoglobin variants, with an unusually high affinity for oxygen, allowing them to extract small amounts from the minimal levels available. They don't venture deeply into the toxic waters below, but they use the upper boundary effectively, exploiting a niche where competitors are scarce. Sometimes, researchers report seeing flashes of movement that don't resemble any known creature in the region. These fleeting shapes vanish before identification becomes possible. Whether they are rarely observed species or tricks of light in the chemically dense water remains a matter of speculation. Blue holes remain poorly studied compared to most marine systems, and each new expedition uncovers organisms that redefine what we expect from isolated environments. In the deepest sections accessible to divers, large animals become rare, but the adaptations to darkness become even more pronounced. The creatures here move as though navigating familiar hallways rather than open water. They tuck themselves into recesses carved into the limestone. They emerge slowly, sensing the environment before taking the next step. Their pale bodies hover in the water like unfinished sketches. Their movements reveal efficiency so complete that nothing appears wasted. If you remain still long enough, you'll see how these creatures organize their activity around the subtle rhythms of the pit, rather than any external cues like daylight or tides. They do not rely on circadian cycles. They have no need for internal clocks tied to the rising and setting of the sun. Their sense of time comes from chemical changes, temperature fluctuations, and the slow drift of organic matter descending from above. This way of experiencing the world is difficult for humans to imagine because our biology ties us to light in so many ways. But for creatures adapted to this darkness, time passes differently. It stretches, slows, and aligns with the gentle patterns of the environment. As you drift farther downward, the water becomes even more opaque, and the darkness transitions from a lack of light to a complete absorption of it. The creatures here do not flee from your beam because it means nothing to them. Their world is defined by touch, pressure, chemistry, and the faint movements of water. The collapse of light changes not only how they hunt and move, but how they interact with one another. Communication between individuals likely occurs through chemical cues or subtle pressure changes rather than visual signals. Nothing in this environment attempts to recreate the functions of light. There are no bioluminescent displays here because the chemistry of the water tends to suppress such activity, and the metabolic cost would outweigh the benefit. There are no bright markings for mating or territorial displays. Everything that persists has done so by abandoning the complexity associated with sight and embracing simplicity in sensory design. Even though the darkness deepens, the environment continues shifting below, where the layers of the blue hole narrow again in chemical composition. The creatures adapted to eternal midnight give way to an even stranger domain where biology becomes sparser and chemistry begins to dominate entirely, shaping a new transition in the descent. As you move through the deeper darkness and settle into the slow rhythm of the pit, a new realization takes shape. Everything down here is arranged not just in layers, but in layers so precise and so finely calibrated that the entire blue hole behaves less like a single ecosystem and more like a vertical stack of separate worlds. Each one functions with its own rules, its own chemistry, its own community, and its own strategies for survival. From above, the water appears uniform. Once you enter, the differences reveal themselves quietly. Every shift in depth introduces a new society of life, and each society depends on the stability of the one above and below it. Instead of spreading outward like reefs, grass beds, or coastal ecosystems, life in a blue hole arranges itself vertically. These boundaries aren't marked by physical barriers, they're drawn by chemistry and the limitations of metabolism. It's hard to appreciate how exact these boundaries are until you drift through them slowly. Nothing announces the transition. There are no visible walls or distinct edges. Instead, the shift appears in the behaviour of the organisms around you. A few metres higher, certain crustaceans thrive. A few metres lower, they vanish completely. Microbial mats cling to specific strips of rock instead of spreading evenly. Tiny drifting organisms accumulate in narrow sections where chemical energy becomes available, creating thin but dense congregations suspended in water that looks empty until a beam of light reveals the haze. These vertical ecosystems form because every inch of depth influences the chemistry of the water. The deeper sections collect hydrogen sulfide produced by decaying organisms. The upper sections hold the last traces of oxygen drifting in from the surface. In between lie transitional zones where both substances interact. The gradients between these layers become living environments. Microbes equipped to thrive on the final remnants of oxygen occupy the upper boundary. Below them, microbes designed for sulfur-rich conditions take over. Even their byproducts become food for microbes in the next layer. The result is a stacked arrangement that resembles the organisation of a sediment core but built out of living cells. If you hover at the boundary between two of these invisible layers, the water feels the same, but the organisms behave differently. Light scatters in new ways. Particles drift in patterns that hint at what biochemical reactions dominate this depth. In the layer where sulfur-oxidizing bacteria flourish, you may notice small flecks drifting upward as byproducts form. In the layer above, the water appears slightly clearer as the chemistry changes again. This stacking effect creates miniature ecosystems so self-contained that species may never travel more than a few meters up or down in their entire lives. This vertical structuring doesn't apply only to microbes. Larger organisms also position themselves according to these chemical boundaries. Predatory crustaceans that hunt at the edges of the sulfide layer rarely enter the higher oxygen zones because their prey stays close to the chemical conditions they need. Fish adapted to the darker areas below the microbial cloud seldom swim upward into clearer water because their sensory systems favour pressures and concentrations found only at specific depths. Even worms embedded in the walls of the pit occupy precise vertical bands. Their presence maps the gradient of chemicals diffusing there, each species occupying the range they can tolerate. It becomes clear that these ecosystems are not overlapping communities competing for space. They are stratified arrangements, each with its own narrow but stable niche. The organisms within them do not cross these invisible borders except by accident. When they do, survival becomes difficult. A few meters of vertical displacement can separate a species from the chemical gradient that sustains it. This makes blue holes some of the most finely partitioned natural environments we know, where the distance between life and death can be measured in the height of a doorway. When scientists lower instruments through a blue hole, the readings change sharply from one depth to the next. The sensors reveal sudden drops in oxygen, abrupt increases in sulfide, spikes in certain nutrients, shifts in salinity, and changes in temperature. But these numbers only hint at the complexity. For the organisms living here, these gradients determine everything. A microbe that thrives at the upper edge of the sulfur boundary depends on receiving just enough oxygen to drive its metabolism. Only a meter lower, that oxygen vanishes. A meter above, the sulfide concentration becomes too low to power the reactions. That organism exists in a narrow world where both requirements meet. Without that thin strip, it would not survive. The same principle applies to the small crustaceans drifting in the layer between the microbial cloud and the deeper anoxic water. They feed on organic particles falling from above, but they avoid the densest sulfide concentrations below. If they drift too high, they lose access to the prey items that accumulate only in the boundary zone. Over generations, they become specialized not just to a type of environment, but to a specific depth range, developing sensory and metabolic traits that fit that range alone. You begin to see how the entire blue hole becomes an arrangement of stacked niches. Nothing here is random. Nothing spreads evenly. Life lines up in thin slices, each slice defined by chemistry rather than geography. If you could cut the blue hole in half and view it from the side, the distribution of organisms would look like narrow-coloured bands on a chart. But from inside, the transitions feel smooth. The water doesn't change colour. The pressure difference is negligible. The visual cues remain minimal, only the life itself changes. This vertical structuring seems unusual compared to coral reefs where species overlap broadly. But in truth, vertical partitioning exists in many environments. Blue holes simply exaggerate it to an extreme level. In the open ocean, plankton arrange themselves by light availability. In deep sea trenches, certain organisms remain above or below particular chemical vents. In caves, species separate based on humidity or nutrient availability. Blue holes amplify this pattern until every few meters create conditions distinct enough to support unique biological communities. Because the boundaries aren't physical, the organisms enforce them through adaptation. Their preferences and tolerances become the architecture of their ecosystems. This creates a series of stable layers that remain predictable over long periods. Unlike shallow ecosystems where storms or currents can alter everything within hours, the deeper parts of a blue hole can remain unchanged for decades. The creatures living in each vertical band depend on that stability, and in return, they contribute to it by reinforcing the chemical structure around them. Consider how the microbial mats influence the layers. They consume hydrogen sulfide and release sulfate. They alter pH. They produce organic material that fuels organisms above them. They slow the diffusion of chemicals into other layers. Their very presence reinforces the boundary by shaping the chemistry locally. Without the microbes, the chemical gradients would smooth out over time. But because these organisms actively maintain the transitions, the boundaries sharpen and remain defined. Life becomes the architect of the vertical structure. In some blue holes, especially those with complex cave systems branching off the main pit, the vertical structure becomes more elaborate. Water flowing in from underwater chambers enters at specific depths, carrying different chemical signatures. This adds complexity to the layers and introduces new microhabitats. The incoming water might contain slightly higher salinity or trace amounts of other compounds. Microbes adapt to these variations, forming additional layers along the vertical gradient. The result is not a simple stack of 3 or 4 ecosystems, but a finely subdivided column containing dozens of distinct microzones. This subdivision explains why new species are often discovered in blue holes. The narrow vertical bands isolate populations from one another, reducing genetic exchange. Over long periods, organisms adapted to one vertical layer diverge from those in layers above or below. Under normal circumstances, such divergence might lead to competition or displacement. But blue holes offer a structure where these populations never overlap enough to interfere. In many cases, species evolve unique traits because their vertical zone demands them. Their ancestors might have lived slightly higher or lower, but over thousands of years their descendants remain anchored to precise gradients of sulfide, oxygen, or nutrients. Another consequence of this vertical arrangement is how it shapes energy flow. Instead of moving laterally across a wide area, energy moves downward. Organic matter begins near the surface, then sinks slowly through the layers. Each layer takes what it needs. Microbes near the boundary convert part of it. Crustaceans feeding just below extract nutrients from particles that become coated with microbial byproducts. Scavengers in deeper zones break down what reaches them. Nothing moves horizontally because the environment lacks current strong enough to carry nutrients sideways. The entire system functions like a vertical conveyor where each step depends on the one above. If you observe the water closely at the boundary between 2 layers, you may notice how slowly particles fall. In the open ocean, gravity pulls particles down steadily until they reach strong currents that scatter them. Here, the stillness of the water allows particles to drift gently. As they fall, they mix with microbes, pick up chemical traces and change composition. By the time they reach the deeper layers, They have transformed multiple times, becoming resources for organisms that cannot live in the upper zones. Every layer modifies the materials passing through it. This creates a cascade effect where organisms in deeper layers depend not on the original particle, but on the transformed version produced by the layers above. This vertical dependency resembles nutrient cycling in soil profiles. What starts as leaf litter becomes humus, then becomes mineral-rich soil layers, feeding organisms occupying different depths underground. Blue holes follow the same principle, but apply it to water instead of soil. The stability of the chemical gradients allows this slow, deliberate cycling to continue without disruption from storms or seasonal mixing. Even the walls of the blue hole contribute to the vertical architecture. Limestone dissolves differently at different depths, depending on pH fluctuations and chemical interactions. This creates subtle changes in texture that influence where microbial mats attach, where crustaceans hide, and where fish choose to rest. Over long periods, these microhabitats reinforce the vertical boundaries by offering consistent surfaces adapted to each layer's needs. The walls become part of the stratification, shaping the communities in 3 dimensions. Occasionally, external disturbances reach the pit. Heavy storms may push surface water slightly deeper, altering the oxygen boundary temporarily. But these disturbances rarely penetrate the deepest layers. The vertical ecosystems reset quickly as the chemistry restabilizes. The organisms here seem prepared for minor disturbances, because their environment has been isolated for so long that it snaps back to equilibrium without much delay. As you continue downward, you experience each layer not as a break from the previous one, but as a slow shift into new biological logic. Nothing distinguishes the boundaries visually, yet the transitions shape everything living here. The deeper zones continue the pattern, stacking new layers shaped by chemistry even more extreme, guiding the organisms that inhabit them and preparing the groundwork for the next section of the descent. As you continue downward past the finely stacked boundaries of life, another quality of the blue hole becomes impossible to ignore. It's something you've sensed for a while, though it's difficult to describe clearly. Nothing moves loudly here. Nothing vibrates the water the way larger animals do in open seas. Even your own equipment feels quieter, as if the environment is absorbing the sound before it spreads. This silence isn't an absence of sound in the usual sense. It feels engineered by the structure and chemistry of the pit. The stillness becomes so complete that it almost gains its own presence. In most places underwater, your ears and bones detect layers of muffled noise, currents, snaps of crustaceans, distant calls of fish, the hum of surface waves. Down here, none of those exist. The blue hole silences them long before they can reach this depth. The result is a space where sound does not behave the way you expect. It changes from a tool into something unfamiliar. At first you might assume that silence in a place like this would be peaceful, but as you hover and listen, you realize the silence is more than quiet. It's structural. The still water, the density gradients, the layers of microbial haze, and the unusual chemistry combine to dampen vibrations so effectively that sound waves barely travel. A small click from your gear seems to disappear instantly, rather than echo through the chamber. Even the faint rumble you might make while exhaling through your regulator transforms into a soft clouded tremor swallowed up before it reaches the walls. This gives the impression that you're suspended in a space with no distance. Sound doesn't travel far enough to reveal the size of the pit. The darkness hides the walls visually, and the silence hides them acoustically. In open water, sound travels much faster and farther than in air. Marine animals rely on this, sending signals across long distances. Whales communicate through kilometers of ocean. Sharks hear heartbeats from meters away. Reef environments crackle constantly with biological noise. In shallow caves, echoes bounce off walls, giving divers a sense of confinement. A blue hole removes all these familiar cues. The sound profile here resembles a vacuum chamber more than a cave or ocean basin. The lack of turbulence, the absence of animals that produce loud noises, and the peculiar chemistry of the water combine to create a soundscape, or something close to the opposite of one, that has no parallel. The deeper you go, the more the structure of silence becomes noticeable. You begin to realise that most underwater environments produce some kind of acoustic signature, even if subtle. There is usually a faint hum from distant activity or small shifts in water pressure that the ears interpret as background sound. But here, those cues vanish. When you pause your movement entirely, the silence becomes so complete that your mind strains to interpret it. Humans rely heavily on environmental noise unconsciously. Even in quiet conditions, we hear something. Air moving through our ears, our own heartbeat, or distant vibrations. Down here, none of these propagate the same way. The silence becomes so deep that your brain almost tries to fill in the missing information, producing imaginary sounds that aren't really there. This has a psychological effect on divers who explore these depths. Some describe a feeling of floating in a void. Others report feeling disoriented because, without sound cues, it becomes difficult to sense whether they are ascending or descending. Vision also becomes unreliable due to the darkness and the scattering caused by sulfide layers. Movement becomes the only way to perceive direction. When you move, your equipment produces faint vibrations, and those vibrations give you a sense of space. Not because they echo, but because the water resists them differently at different depths. But when you stop, the sensory feedback disappears. Meanwhile, the creatures that live here operate entirely within this soundless framework. They do not rely on calls or clicks. They do not use sound to find one another or ward off predators. Their sensory organs have developed around pressure detection, chemical gradients, and proximity-based cues. For them, the silence is not unusual. It is the only environment they know. If sound were introduced suddenly and strongly, they would likely interpret it as a threat. A large animal entering from outside would distort the water with vibrations long before it became visible. But those moments are rare. The pit isolates its inhabitants from the outside world not by walls or currents, but by muffling the one medium through which many marine creatures communicate. At this depth, sound waves behave differently for several reasons. The density of the water changes due to temperature and chemical composition. Hydrogen sulfide alters how vibrations move, absorbing or scattering them. The vertical gradients in the blue hole create subtle variations in density that deflect sound rather than carrying it smoothly. Layers of suspended particles act as tiny dampeners. Each particle vibrates slightly when hit by a sound wave, absorbing energy and diminishing the wave before it can travel farther. The result is sound that fades within a meter or two. Even small echoes do not return. The walls remain silent. The ceiling remains silent. There is no feedback loop. The silence also affects how some organisms hide or hunt. Without sound, there is no acoustic signature to give away their presence. Pressure waves still reveal movement, but only at close range. A predator in this environment must rely on subtle detection rather than distance. Prey species benefit from this too. They do not need to quiet their movements. They simply need to minimize sudden pressure disturbances. The entire ecosystem functions on silence not because it values quiet, but because sound cannot travel effectively. For the organisms here, silence becomes a habitat condition as fundamental as salinity or temperature. In regions slightly above this depth, where a faint amount of light still filters downward, you might see drifting particles responding to vibrations caused by your presence. But down here, where the silence dominates fully, even those subtle movements diminish. The density of the water combined with the thickened chemical composition slows particle motion. This contributes to the eerie stillness. Particles fall slowly, settling in gentle spirals rather than direct paths. Without turbulence or sound, the water column becomes a place where nothing interrupts the descent of organic material. The silence extends into motion itself. It isn't just that nothing makes noise, nothing moves in a way that would create noise. When scientists deploy equipment to record sound in blue holes, the instruments often return long stretches of data filled with almost no detectable acoustic activity. Occasionally a faint pop appears in the recording, possibly a tiny crustacean snapping its appendages, but these are rare. More commonly, the sensors detect subtle hums generated by the instruments themselves or the divers using them. Once the equipment is still, the readings flatten. In the deepest parts of the pit, the line on the graph becomes so steady that it resembles the output of a device that has been turned off. Yet the conditions are entirely natural. The pit simply has little to give acoustically. Because silence dominates so thoroughly, even internal sounds feel exaggerated. Your heartbeat seems louder. Your breathing seems more forceful. Your exhalation bubbles reverse the silence momentarily, only to be absorbed quickly. Every sound you produce becomes isolated, without the masking effect of environmental noise. This creates a strange feedback loop where your mind becomes more aware of your internal noises than your surroundings. Divers sometimes describe the sensation as hearing themselves from within, rather than hearing the environment outside. This experience contrasts sharply with diving in open water, where external sounds always blend with personal ones. In blue holes, the external world rarely adds to the soundscape. This puts focus on your own presence. Every movement becomes significant. Every sound you make becomes a reminder that you are an anomaly, in a place built around silence. The creatures around you notice this too. Their sensory organs detect your movements as pressure shifts, but they do not respond with fear unless the disturbance is abrupt. They have survived generations in a world that rewards minimal motion and quiet precision. Your presence introduces a new pattern they must interpret carefully. If you move slightly closer to the walls, the silence becomes even more pronounced. The rock absorbs vibrations better than open water. Microbial mats lining the limestone dampen sound by trapping small pockets of water and absorbing energy through their dense structures. Each patch of microbial life acts like acoustic insulation. In caves above ground, sound bounces off bare stone, amplifying or echoing. Here, the mats eliminate echoes before they begin. Even if you tap the wall, the vibrations remain local. They dissipate into the rock and water without returning. This creates a unique form of sensory isolation, where even the environment refuses to speak back. Some researchers refer to this condition informally as acoustic invisibility. It means that unless you intentionally produce strong vibrations, you might as well not exist acoustically. Your presence doesn't travel. You leave no auditory signature. For the creatures living here, this is normal. They evolved in a world where silence isn't the absence of sound, but the foundation of existence. They developed strategies that rely on touch, chemistry, and pressure. Their senses focus on information that doesn't diminish within the first meter of travel. Even though this silence dominates, it doesn't eliminate all forms of communication. It simply shifts communication into realms humans rarely perceive. Chemical signals travel more effectively in still water. Some organisms release chemical cues used to signal territory, attract mates, or coordinate behavior. These signals don't rely on sound waves, so they move through the layers regardless of the silence. Pressure-based signals also function effectively. The slightest motion from an animal can transmit information to another only a short distance away. In an environment where you can't speak through sound, you learn to speak through displacement and molecules instead. The silence might lead someone to think that life becomes less active as depth increases. But the opposite is often true. The creatures here must constantly interpret the limited signals available. They become more attuned to vibration patterns than fish in open water. They learn to detect disturbances caused by falling particles. They recognize the stir of water produced by another creature adjusting its position. Even microorganisms respond to chemical cues released by neighbors. Silence doesn't weaken the ecosystem, it sharpens its focus. Because the silence is so complete, it affects scientific study. Researchers attempting to map the structure of a blue hole using sonar find the readings distorted or muted by the water chemistry. Sound pulses don't bounce back clearly. Instead of defining the shape of the walls, the device returns ambiguous data. Mapping must often rely on visual or tactile methods, rather than acoustic ones. This adds mystery to the deeper chambers. Some regions remain poorly mapped because sound-based tools fail in the environment. The deeper you descend into the quiet, the more you sense that the silence acts not just as a condition, but as a boundary. It separates the upper world from the lower, not physically but perceptually. In the world above, sound carries stories. It reveals motion, distance, and energy. Down here, silence erases those stories before they form. The environment becomes self-contained. Creatures live in close proximity without needing to announce themselves. The vertical boundaries remain reinforced through chemistry and pressure rather than sound. As you hover in this silent domain and prepare to move deeper still, the environment changes again. The silence remains intact, but the chemistry grows heavier. The particles thicken and the boundaries tighten further. You move toward layers where even the pressure-based cues become softer, where the silence deepens into something that shapes not only behavior, but survival in ways the next layer will reveal as you continue the descent. As you continue downward through the silent layers, something changes slowly enough that you might miss it at first. The water feels heavier, not thicker in the physical sense, because the density difference isn't enough for your body to register, but heavier in the sense that the entire environment seems to brace against movement. The silence remains, but it takes on a slightly different character, as though the pit itself is holding something in place. This is where the structure becomes more unstable, not in terms of collapse, but in terms of hidden energy. Beneath this depth, where light has fully surrendered, and where chemical gradients dictate who survives, the blue hole holds pockets of gas and accumulated compounds waiting quietly for something to disturb them. These deeper layers don't simply sustain life. They contain forces that can shift the entire environment in an instant. The sea, in these regions, can turn against itself. Upwellings in blue holes do not behave like the ones found in coastal regions or open oceans. They are not driven by wind patterns, temperature gradients, or surface currents. Instead, they come from chemical instability buried deep within the column. When gases trapped in sediments suddenly release, or when water layers begin to mix due to subtle disruptions, the entire structure can change quickly. It isn't a violent eruption, but a rising plume of altered water that sweeps upward through the pit with silent precision. This plume carries hydrogen sulfide, methane, carbon dioxide, and other dissolved compounds that have accumulated over years or decades. To organisms adapted to stable conditions, this upward surge can be lethal. At these depths, gases accumulate because decomposition occurs without oxygen. Organic matter that settles at the bottom breaks down slowly, producing methane and other byproducts. Hydrogen sulfide builds steadily in the water as microbes metabolize sulfur compounds. These gases become trapped within the sediments or form pockets along the walls. Under normal conditions, they remain sealed in place by pressure and by the chemistry of the surrounding water. But when something shifts, a diver's fin stroke, a change in temperature, a rock falling from above, or an internal chemical imbalance, the pockets may release suddenly. Even a minor discharge can send a pulse of toxic water upward. From your perspective as you hover here, these upwellings remain invisible until the water in front of you starts to drift upward in a slow, eerie column. The particles suspended in it reveal the movement before the chemistry does. They rise instead of fall. They swirl in delicate patterns as they enter layers of water with different density and temperature. The motion is gentle, but the change it brings is profound. Organisms living above this point depend on the stability of chemical gradients. When those gradients shift, the boundaries that define their vertical ecosystems break down. The organisms cannot adjust quickly enough. A crustacean positioned carefully in the narrow oxygen-poor but sulfide-light layer may suddenly find itself in water far too toxic for survival. A fish adapted to borderline oxygen conditions may encounter water devoid of oxygen altogether. In extreme cases, entire communities can collapse temporarily. These events do not destroy the ecosystem permanently, but they reset the structure. Microbes repopulate quickly, crustaceans return as conditions stabilize, the boundaries reform. But in the moment of disruption, the pit becomes a vertical conveyor of toxicity moving in the wrong direction. The sea, in this moment, folds inward against its own inhabitants. Scientists monitoring blue holes have seen spikes in hydrogen sulfide concentration well above expected layers. These spikes reveal that trapped sulfide water sometimes rises with enough force to alter conditions dozens of meters above. The force isn't mechanical. It doesn't churn or create turbulence the way a geyser might. Instead, it moves in a soft, upward drift that appears calm but carries lethal chemistry. The danger lies in its subtlety. The physical environment encourages these trapped gases to form. Near the bottom, the sediments contain thick layers of organic material that have accumulated over centuries. The microbes feeding on this material work slowly, producing gases that have nowhere to escape. The lack of oxygen slows decomposition. The temperature remains relatively stable. Pressure increases gradually with depth. This combination forms pockets where methane and carbon dioxide gather in concentrations far higher than the surrounding water. These pockets remain sealed beneath layers of finer sediment. Sometimes they dissolve slowly into the water. Sometimes they remain trapped for years. The limestone structure also plays a role. Cracks and crevices within the walls collect gas bubbles. These cavities act like reservoirs. When a bubble becomes large enough, the pressure difference between the cavity and the water column weakens. The bubble escapes. It dissolves rapidly into the surrounding water, altering the chemistry instantly. The gas release triggers small pressure changes that push water upward. It isn't violent, but the chemical impact reaches far. In open ocean systems, these releases disperse quickly. Currents dilute the gases. Waves mix the water. The environment stabilizes within minutes. In a blue hole, nothing dilutes quickly. The layers remain separated by density, salinity, and temperature. A gas release can remain trapped within a layer, traveling upward slowly without mixing across the entire column. This creates narrow plumes of altered water that remain coherent for long periods. Organisms drifting into the plume encounter chemistry they are not built to handle. You might expect that the creatures living here would evolve ways to avoid these upwellings. Some do. Fish with heightened pressure sensitivity respond quickly to small disturbances in water movement, fleeing before the plume reaches them. Crustaceans sense the chemical shift and retreat sideways into crevices. Microbes simply shift metabolic pathways or survive within broader chemical tolerances, but survival depends on the scale of the event. A small upwelling may wipe out only a small cluster of organisms. A large release can reset an entire vertical ecosystem. These events don't happen regularly. They depend on long-term accumulation of gas and on the occasional disturbance. Storms can influence conditions indirectly by increasing mixing near the top layers. Earthquakes can disturb sediments. Even subtle shifts in temperature can destabilize gas pockets. But because the pit remains so isolated from outside forces, gas buildup continues steadily, forming these silent threats that wait below. Divers exploring deeper sections sometimes notice small plumes rising in slow spirals. They appear as slightly lighter or darker sections of water, depending on the concentration of particles. These spirals do not produce danger for someone carrying an external air supply, but they reveal the dynamic nature of the deep layers. Even if the water appears motionless, the chemistry never stops changing. Hydrogen sulfide continues producing. Methane continues accumulating. Organic matter continues breaking down. Everything contributes to a slow tension that occasionally resolves itself through a release. One of the more unusual consequences of these conditions is the presence of layers where oxygen can appear suddenly in trace amounts. Some upwellings pull water down from slightly higher layers as they rise, mixing just enough to produce curious anomalies. These anomalies rarely last long but indicate how sensitive the system is to small shifts. In most parts of the ocean, mixing is constant. In a blue hole, mixing becomes an event rather than a normal process. The deeper you drift, the more you sense that the environment is holding something beneath you. The water around you remains calm, but the knowledge that layers of toxic compounds and trapped gases lie below creates tension. It becomes easier to understand how these vertical ecosystems form and collapse. Everything relies on stillness. Nothing in this environment works if the layers mix freely. The organisms survive because the boundaries remain intact. When the sea disrupts its own boundaries, the system temporarily turns against its inhabitants. Researchers studying blue hole chemistry often track carbon dioxide concentrations. CO2 behaves differently in anoxic environments. It dissolves into the water until the saturation point becomes high. When water becomes supersaturated, any disturbance can cause CO2 to come out of solution as microbubbles. These microbubbles accumulate, join together and rise. As they rise, they pull water with them, altering density gradients further. This process explains some of the narrow plumes divers observe. CO2 doesn't create toxicity the way hydrogen sulfide does, but it changes the pH enough to disrupt microbial activity temporarily. Methane also behaves in interesting ways. It accumulates in sediments until a disruption releases it upward as a cloud of dissolved gas. Methane oxidation in oxygen, pore zones, is slow, allowing it to remain in the water column longer. When the methane-rich water rises, it carries chemical signatures that organisms near the boundary analyze unconsciously. Some avoid these plumes, others feed on microbial blooms triggered by the methane. Even harmful events create new opportunities. The most dangerous gas remains hydrogen sulfide. High concentrations can kill complex organisms almost instantly. Small changes in concentration can disrupt metabolic processes. In humans, hydrogen sulfide is lethal at surprisingly low levels because it interferes with the electron transport chain in cells. For marine animals, the effects are similar. Those adapted to borderline conditions tolerate small amounts. But when an upwelling brings a dense mass of sulfide-rich water upward, nothing adapted to higher layers can survive prolonged exposure. Despite this danger, the pit continues functioning. The organisms return. The boundaries re-establish themselves. The system resets. This resilience comes not from robustness, but from specialization. Each layer has organisms capable of recolonizing quickly. They reproduce rapidly. They exploit the chemistry efficiently. The vertical ecosystems rebuild themselves because the conditions that support them remain stable most of the time. If you imagine standing at the rim of the blue hole and looking down, these events remain invisible. The water appears calm. The surface may barely ripple. But beneath, the pit contains energy stored as chemical potential. It is not the explosive energy of geothermal vents or volcanic eruptions. It is quieter, slower, and more subtle. The danger comes not from heat or pressure, but from a structure built on separation. Once separation breaks, the consequences ripple upward. The creatures that live near this depth understand these risks in ways humans cannot. Their sensory systems evolve to detect small changes that precede upwellings. A shift in pressure, a subtle increase in particle movement, a faint chemical change drifting upward. These signals tell them to retreat into cracks or ascend slightly to avoid the rising plume. Their survival depends on recognizing the earliest signs. Even so, not all survive. These events remain part of the natural rhythm of blue holes, shaping who lives and who doesn't. As you hover in this deeper region and prepare to descend farther, you sense an even greater stillness below. The layers thickened by gases and decades of chemical accumulation give way to new conditions forming in the darkest and most secluded depths of the pit, where the final environment waits quietly, held together by pressure and time, revealing what remains when the sea becomes almost entirely still. As the darkness anchors itself fully around you, and the last traces of movement drift beyond reach, the space below begins to take on a different meaning. The deeper layers of the blue hole aren't just another step toward the bottom. They are the point where everything that came before settles into its final arrangement. The silence remains, the chemistry grows heavier, the boundaries sharpen into delicate partitions, and the entire environment becomes a kind of suspended world where time slows enough for the past and present to overlap. Down here, survival becomes less about enduring adversity, and more about understanding how life shapes itself when every advantage disappears. The blue hole reveals something subtle that only becomes clear when you reach this depth. It shows how life survives not by overpowering its environment, but by yielding to it so completely that each organism becomes an extension of the conditions around it. At this depth, even the gas pockets and chemical plumes you encountered earlier grow less frequent. The water becomes thick with dissolved compounds that have accumulated for decades. Organic material drifts downward until it reaches this layer, where it settles and becomes part of a slow cycle that operates without urgency. The creatures adapted to these darkest regions are few, but each one represents a lesson in endurance. They do not compete aggressively, they do not flee quickly, they do not waste energy on unnecessary structures. Every part of them reflects the demands of their environment. They survive because they inhabit a world where simplicity becomes a strength. If you look at the walls closely, the limestone here shows fewer signs of disturbance than above. The formations look older, smoother and more worn. Chemical reactions occur slowly at this depth, but they leave their marks over centuries. Once the cave system was dry, and mineral deposits grew like roots from the ceiling and walls. Now, submerged in poisonous water, they remain frozen in place. What you see here is a mixture of geological history and biological persistence, held together by conditions that would collapse ecosystems elsewhere. It becomes clear that survival in this depth depends not on resisting the environment, but on being shaped by it. The few animals that live near the bottom show this principle clearly. Many of them appear incomplete by surface standards. Their bodies lack pigmentation, their eyes shrink or disappear, their skeletons soften, their movements slow. But none of this represents weakness. These traits are adaptations that allow them to function when energy is scarce and sensory information is limited. The creatures that remain here are the ones that learned how to survive with less rather than more. They embody efficiency so complete that it seems almost purposeful. Their feeding habits reflect the same pattern. They do not forage widely, they do not chase prey. Instead, they wait near zones where organic particles gather. Microbes break down those particles, creating chemical cues that guide the animals toward food. The entire ecosystem becomes a chain of slow, deliberate interactions. Even the microbial mats participate in this rhythm. They feed on chemicals in the water, grow slowly, and release byproducts that feed other organisms. Nothing in this layer moves quickly, but everything moves steadily. There are no sudden bursts, no dramatic shifts, no chaotic hunts. Everything operates within a narrow margin of energy, balanced exactly enough to continue. You might expect a harsh environment like this to push life to its limits, but what you see instead is something more disciplined. Life down here doesn't struggle against the conditions. It adapts so deeply that the boundary between organism and environment becomes almost invisible. The microbes demonstrate this most clearly. They occupy niches defined by chemical gradients so specific that they form sheets along the walls, each layer reflecting a different metabolism. They do not compete broadly. They find the narrowest possible niche and optimize it. In doing so, they help stabilize the environment for everything else. The idea that extreme environments destroy life is common, but the blue hole shows a different narrative. It reveals that life can flourish even when resources are limited and conditions toxic. It does so by reducing energy demands, simplifying structures, and relying on relationships rather than dominance. The vertical ecosystems above reflect the same principle. Each organism survived by finding a zone where it could function with the least resistance. The predators in the mid-layers show patience instead of power. The crustaceans rely on sensory precision rather than speed. The fish hover quietly rather than swimming constantly. Every behaviour becomes a strategy moulded by scarcity. The silence in these depths reinforces this idea. Without sound, life cannot rely on acoustic cues. Without light, vision becomes irrelevant. Without oxygen, energy production slows. Without mixing, resources arrive unpredictably. And yet life continues, not by overcoming these limitations, but by incorporating them into its structure. This environment doesn't eliminate life, it edits it. When you remain still and let your light fade slightly, the creatures continue their work without noticing you. Their movements remain unhurried. Their sensory tools extend and retract gently. Their bodies drift in small arcs shaped by tiny water movements you barely detect. If a particle falls through the water column, a nearby crustacean might sense it through pressure differences and adjust its posture. If a microbial mat grows slightly thicker, a feeding grazer might shift position. These interactions demonstrate how survival here depends on being attuned to the smallest possible changes. The deeper region also reveals something about how ecosystems operate when isolated for long periods. Without external disturbances, the structure becomes a closed loop. Organic matter sinks, microbes break it down, chemicals diffuse upward, predators feed on organisms that feed on microbes. The chemistry becomes both the product and the controller of life. This loop continues for as long as the environment remains stable. It does not expand like a reef or contract like a tide pool. It simply persists. By observing these layers and how creatures behave in them, you begin to understand how survival becomes a form of cooperation between the organism and its environment. A blue hole's isolation creates a selective pressure, unlike anything in the open sea. Only those organisms that can reduce their metabolic needs, adapt their sensory methods, and optimize narrow niches remain. The rest vanish quickly. This creates a kind of natural filter that reveals what strategies truly support long-term survival. Some researchers use blue holes as analogues for early Earth. The chemistries match ancient oceans in many ways. The microbial communities resemble lineages that may have existed billions of years ago. The lack of oxygen mirrors a time before complex life emerged. In that era, survival depended on similar strategies: metabolic efficiency, low energy consumption, chemical dependence rather than oxygen dependence, and stability rather than mobility. Observing these miniature versions of ancient ecosystems helps explain how life persisted through harsh global conditions long before the planet became hospitable. The deeper you reflect on these patterns, the more you notice how much survival depends on balance rather than conflict. Surface ecosystems often portray survival as a battle between organisms. Down here, survival depends on avoiding unnecessary conflict. The organisms conserve energy by not competing aggressively. They thrive by fitting perfectly into available niches. They persist by minimizing waste. Every adaptation supports this philosophy. Reduced vision saves energy. Slower movement conserves calories. Specialized metabolisms exploit energy sources that other organisms ignore. Even silence benefits them by allowing pressure-based detection systems to function clearly. If you could observe this ecosystem over centuries, you would see how it remains stable not because nothing changes, but because changes occur slowly enough for organisms to adapt. Gas releases disrupt layers occasionally, but recovery follows. Organic matter supply fluctuates, but microbes adjust. Chemical boundaries shift slightly, and organisms track those changes through sensory cues. This ability to respond to long-term shifts without collapsing defines resilience. It shows that survival doesn't require ideal conditions, it requires adaptability. As you continue hovering in this depth, the sense of suspended time becomes stronger. The water does not churn. The boundaries do not blur. The creatures move as if the world is unhurried. Yet beneath this stillness, Countless biochemical reactions occur every second. Microbes divide, process sulfur, convert carbon, build structures, and break down organic material. Crustaceans digest particles. Fish adjust their position. Worms extend into cracks and retract slightly. Everything contributes to the quiet stability. The deeper layers also reveal something about the relationship between life and death in extreme environments. Organic matter becomes food. Dead organisms create new chemical gradients. Microbial blooms follow small disturbances. Predators feed on weakened or drifting animals. Decomposition becomes slower, but it becomes more efficient. Nothing is wasted because everything is needed. This recycling of life into chemistry and chemistry into life becomes the backbone of the entire system. The sensation of reaching the lowest accessible point is not one of finality. It feels more like a pause. You begin to recognize how each part of the pit builds on the previous one. The microbial haze supported crustaceans. The crustaceans supported predators. The predators supported nutrient cycling. Gas plumes altered chemistry that microbes adapted to. Everything influences everything else, but not in a chaotic way. The stability of the environment moderates the interactions, creating a structure that remains coherent even as individual moments shift. As you prepare to ascend eventually, slowly, deliberately, you begin to sense that the blue hole has not simply shown how life survives in extreme conditions. It has shown how survival becomes a collaboration between environment and organism. The creatures down here reveal that survival is not always a matter of competition. It can be a matter of refinement, patience, and quiet adaptation. And the layers you pass through on the way upward will reflect the same principle, continuing the narrative without breaking the rhythm that brought you this far.